Picture yourself standing beneath a canopy of stars on a night so clear that the Milky Way stretches across the heavens like spilled milk on black velvet. The universe spreads before you in all its ancient glory. Each pinpoint of light carries stories spanning billions of years. Each flicker whispers secrets of cosmic birth and death. But hidden among these gentle lights lurk monsters beyond imagination. Invisible predators that devour light itself. Places where the very fabric of reality tears apart. Objects so massive, so dense, that they bend space and time into impossible shapes. These are the black holes. The cosmic vacuum cleaners that consume everything. The ultimate mysteries that challenge everything we think we know about existence. Tonight, we embark on a journey into one of these monsters. A journey from which no light, no matter, no information has ever returned to tell the tale. We will follow a path that leads beyond the edge of known physics, beyond the boundaries of human experience, into realms where mathematics becomes poetry and science transforms into philosophy. What would it feel like to fall into absolute darkness? What happens when you cross the threshold between the possible and the impossible? What lies beyond the event horizon, that mysterious boundary where even Einstein's equations begin to whisper in languages we cannot understand? These questions have haunted physicists for generations. They have sparked debates among the greatest minds in science. They have challenged our fundamental understanding of reality itself. Tonight, we will attempt to answer them. Not with certainty, for certainty dissolves in the face of a black hole, but with wonder, with imagination, with the same curiosity that drives us to explore the deepest oceans and the highest mountains. The ancient Greeks believed that looking into the abyss meant the abyss would look back into you. But what happens when the abyss is not metaphorical? What happens when it is a literal tear in space-time, a place where the normal rules of existence cease to apply? What happens when the abyss is a black hole and you are falling toward it at tremendous speed? In the coming journey, we will trace the path from the outermost reaches of a black hole as influence to its innermost secrets. We will experience the gradual warping of time and space. We will feel the increasing pull of gravity as it grows from gentle tug to irresistible force. We will witness the strange dance of light as it spirals into oblivion. But this is not merely a story of destruction. Black holes are creators as well as destroyers. They shape galaxies. They regulate the birth of stars. They may even give birth to entire universes. They are the architects of the cosmos on the grandest scales, the sculptors of space-time itself. As we prepare to take this impossible journey, remember that we are not merely observers. We are participants in the greatest mystery the universe has to offer. We are explorers venturing into territory that exists at the very limits of human understanding. We are witnesses to the ultimate cosmic drama, where matter and energy perform their final dance on the stage of infinity. The stars above continue their ancient waltz, unaware of the invisible monsters that move among them. But we know they are there. We have detected their presence through the gravitational waves they send rippling through space-time when they collide. We have seen the shadows they cast against the bright backgrounds of distant galaxies. We have even photographed one, capturing its silhouette against the glowing matter that spirals toward doom. So let us begin this journey together. Let us fall into mystery. Let us discover what lies beyond the point of no return. Long before we had names for these cosmic monsters, mathematicians glimpsed their existence in the elegant curves of equations. It was 1783 when John Michell, a Cambridge professor with an unusual imagination, first conceived of what he called dark stars. He wondered what would happen if a celestial body became so massive that light itself could not escape its gravitational embrace. Mitchell's dark stars remained curiosities for over a century, mathematical ghosts haunting the equations of Newton's gravity. Few took them seriously. After all, how could something be invisible yet detectable? How could emptiness have mass? How could nothing be something? The universe, however, cares little for human intuition. When Einstein revolutionized our understanding of gravity in 1915, he revealed that massive objects do not simply pull on other objects. Instead, they warp the very fabric of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and marbles rolled nearby will curve toward it. But Einstein's vision was far more radical. Space and time themselves became the curved sheet. Mass and energy became the bowling balls. And the paths that objects follow became the natural consequences of this cosmic geometry. Within months of Einstein's breakthrough, a German physicist named Karl Schwarzschild made a disturbing discovery. While serving on the Russian front during World War I, Schwarzschild solved Einstein's equations for the space-time around a massive, perfectly spherical object. His solution revealed something extraordinary. If enough mass were compressed into a small enough space, it would create a region for which nothing, not even light, could escape. Schwarzschild called this the sphere of gravitational compression. Today, we know it as the event horizon of a black hole. Tragically, Schwarzschild died of an autoimmune disease contracted in the trenches, just weeks after making his discovery. He never lived to see the profound implications of his work. He never witnessed the decades of debate his equations would inspire. He never saw the day when his mathematical prophecy would be confirmed by observation. For years, physicists treated Schwarzschild's solution as a mathematical curiosity. Surely nature would not allow such extreme conditions to exist. Surely there were physical mechanisms that would prevent matter from collapsing to such density. Surely the universe had built-in safeguards against creating regions where its own laws broke down. But nature is under no obligation to conform to human comfort. As astronomers developed more powerful telescopes, they began to observe phenomena that defied explanation. Stars appeared to be orbiting invisible companions with masses far exceeding any known stellar remnant. Violent jets of matter and energy erupted from seemingly empty regions of space. Radio waves poured forth from cosmic sources with no visible origin. The evidence mounted slowly, like shadows lengthening at twilight. Each observation added another piece to a puzzle that physicists were reluctant to solve. The universe was whispering about the existence of objects so strange, so extreme, that they challenged the very foundations of physics. Meanwhile, theorists continued to explore the mathematical landscape that Schwarzschild had first mapped. They discovered that his sphere of gravitational compression was not a physical surface, but a point of no return. An invisible boundary in space-time itself. Cross this boundary, and all possible futures lead inexorably inward. Every path through space-time curves toward the center, toward a point where density becomes infinite and the laws of physics surrender to mystery. It was John Wheeler, the Princeton physicist with a gift for memorable phrases, who finally gave these objects their modern name. In 1967, he declared that dark star and gravitational collapse object were too cumbersome. The universe needed a name that captured both the mystery and the menace of these cosmic predators. Black hole, he said. The name stuck. But naming something and understanding it are entirely different endeavors. As astronomers began to catalog these invisible monsters, they realized that black holes were not merely cosmic oddities. They were fundamental features of the universe. They existed at the centers of galaxies, including our own. They regulated the formation of stars and the evolution of cosmic structure. They were the universe's way of processing matter and energy on the grandest scales. The shadows that bend light had revealed themselves to be architects of reality itself, and humanity was only beginning to comprehend their true nature. Every star begins its life as a cosmic furnace, converting hydrogen into helium through the alchemy of nuclear fusion. For millions or billions of years, these stellar giants maintain a delicate balance between the inward crush of gravity and the outward pressure of nuclear fire. It is a dance of opposing forces, a cosmic tug-of-war that that creates the light and warmth that make life possible. But every dance must eventually end. The most massive stars burn through their nuclear fuel with reckless abandon. They are the cosmic equivalent of sports cars, driven at maximum speed. Beautiful, powerful, and destined for spectacular crashes. While our sun will shine steadily for another 5 billion years, stars 10 times more massive live fast and die young, exhausting their fuel in mere millions of years. Picture a star 30 times more massive than our sun. In its core, temperatures reach hundreds of millions of degrees. Pressures exceed anything achievable on Earth. Under these extreme conditions, the star burns through hydrogen and helium, then carbon, neon, oxygen, and silicon in increasingly rapid succession. Each fusion reaction produces heavier elements and releases tremendous energy, but also brings the star closer to its ultimate fate. The end comes when the star attempts to fuse iron. Iron is the cosmic dead end. Fusing iron requires more energy than it produces. When a massive star's core becomes dominated by iron, the nuclear fire that has sustained it for millions of years suddenly extinguishes. In an instant, the outward pressure that has held the star aloft against gravity disappears. What happens next unfolds with breathtaking speed. The stellar core, no longer supported by fusion pressure, collapses catastrophically. In less than a second, a region the size of Earth compresses to a sphere merely 20 kilometers across. The collapse generates temperatures of billions of degrees and pressures that compress matter beyond the density of atomic nuclei. Protons and electrons are crushed together to form neutrons. The very atoms that once composed the star's core are obliterated. This collapse releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. The shock wave from the core collapse races outward through the star's outer layers, creating one of nature's most spectacular displays, a supernova explosion. For weeks, the dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion hurls the star's outer layers into space at speeds of thousands of kilometers per second, seeding the cosmos with the heavy elements forged in the stellar furnace. These are the elements that will someday become planets and life and consciousness capable of contemplating its own origins. But at the center of this cosmic fireworks display, something even more extraordinary is taking place. If the collapsed core exceeds about 3 solar masses, not even the pressure of neutrons can halt the gravitational collapse. The core continues to shrink, passing through the size of a city, and a mountain, then a building, approaching the realm where Einstein's equations predict something impossible, a point of infinite density and infinite curvature of spacetime. At this moment, a black hole is born. The newborn black hole's event horizon forms instantaneously, expanding outward at the speed of light until it encompasses a sphere, perhaps 50 kilometers across. Everything within this boundary is forever cut off from the external universe. Any light, any matter, any information that falls within the event horizon is doomed to spiral inward toward the central singularity. But the birth trauma of a black hole extends far beyond the event horizon itself. The intense gravitational field warps spacetime in its vicinity, creating effects that ripple outward at the speed of light. If the collapsing star is part of a binary system, its companion may find itself suddenly orbiting an invisible partner that pulls matter from its surface in luminous streams. These accretion streams spiral inward, heating to millions of degrees and glowing with X-ray intensity. The orbital dance of matter around a newly formed black hole creates some of the most energetic phenomena in the universe. Magnetic fields accelerate particles to nearly the speed of light, launching jets of plasma that can extend for thousands of light years. In this way, the death of a single star can influence the evolution of an entire galaxy. The black hole becomes a cosmic engine, converting the gravitational potential energy of infalling matter into radiation and high-energy particles. It shapes the distribution of gas and dust around it, regulating the formation of new stars and planetary systems. Not all massive stars follow this exact path to black hole formation. Some explode so violently that they scatter their entire mass into space, leaving no remnant behind. Others collapse to form neutron stars, objects so dense that a teaspoon of their material would weigh as much as a mountain. But the most massive stars, those exceeding perhaps 20 or 30 solar masses, seem destined to become black holes. As we trace this cosmic life cycle from stellar birth to gravitational collapse, we begin to see black holes not as anomalies, but as natural consequences of physics operating under extreme conditions. They are the universe's way of recycling matter and energy, of creating the most efficient gravitational engines possible, of pushing the boundaries of what reality allows. The birth of darkness, it turns out, illuminates the deepest principles governing our cosmos. Imagine dissecting a monster that exists only as curved spacetime, a creature with no solid surface, no material substance, yet possessing anatomy as precise and complex as any biological organism. The black hole reveals itself not through flesh and bone, but through the elegant geometry of Einstein's equations and the violent ballet of matter dancing at the edge of oblivion. At the heart of every black hole lies the singularity, a point of infinite density and infinite curvature of spacetime, where the known laws of physics break down completely. Here, general relativity meets its match, predicting conditions so extreme that they transcend mathematical description. The singularity is not a place in the conventional sense, or rather the endpoint of spacetime itself, a cosmic full stop where the story of matter and energy reaches its conclusion. Yet the singularity remains hidden from outside observers, veiled behind the event horizon like a cosmic secret too terrible to reveal. The event horizon forms the black hole's most defining feature, an invisible membrane in spacetime that marks the boundary between the possible and the impossible. This sphere of no return expands with the black hole's mass, creating a larger prison for more massive captives. For a black hole with the mass of our Sun, the event horizon would stretch merely 6 kilometers across. But supermassive black holes, those cosmic giants that lurk at galactic centers, can possess event horizons larger than our solar system. These monsters contain millions or billions of stellar masses compressed into regions that dwarf planets yet remain invisible to direct observation. Beyond the event horizon lies another invisible boundary, the photon sphere. Here, at precisely 1.5 times the horizon's radius, light itself can orbit the black hole in perfect circles. Photons that approach at exactly the right angle and speed become trapped in eternal circumnavigation, neither falling inward nor escaping outward. This ghostly shell of orbiting light remains forever beyond our detection. Yet its theoretical existence reveals the intricate geometry of curved spacetime around the gravitational monster. Further outward, we encounter the innermost stable circular orbit, the last refuge where matter can maintain a stable circular path around the black hole. Inside this boundary, no orbit remains stable. Particles spiral inevitably inward, their fate sealed by the relentless pull of gravity. This orbital limit varies with the black hole's rotation, shrinking as the monster spins faster, drawing the final stable orbit ever closer to the point of no return. But black holes rarely feast in isolation. Most attract streams of matter from companion stars or surrounding gas clouds, creating one of the cosmos's most spectacular phenomena, the accretion disk. As material spirals inward, it forms a flattened disk of superheated plasma, glowing with the brilliance of 1,000 suns. Friction between orbital layers heats the disk to millions of degrees, creating temperatures that exceed those found in stellar cores. The inner regions of the accretion disk approach the speed of light as they orbit just outside the event horizon. Here, matter experiences the full fury of the black hole's gravitational field, compressed and heated until it radiates across the electromagnetic spectrum, from radio waves to gamma rays. The disk's inner edge glows white-hot, gradually cooling to red as distance from the black hole increases. Some black holes supplement their accretion disks with even more dramatic displays of power. Magnetic fields threading through the disk and the black hole's ergosphere can launch jets of plasma at nearly the speed of light. These relativistic jets pierce space for thousands of light years, carrying more energy than entire galaxies produce through stellar fusion. The jets emerge from the black hole's poles, creating cosmic lighthouses that can be observed from billions of light years away. The jets form through a process that transforms the black hole as rotational energy into kinetic energy of escaping particles. Magnetic field lines, anchored in the accretion disk and twisted by the black hole's rotation, act like cosmic particle accelerators. They extract energy from the spinning black hole and channel it into narrow beams of high-energy plasma that race away from the gravitational monster at fantastic speeds. Around rotating black holes, space-time itself participates in this cosmic dance. The dragging of space-time, known as the lens-stirring effect, forces everything near the black hole to rotate in the same direction as the monster's spin. This region, called the ergosphere, extends beyond the event horizon and creates a zone where nothing can remain stationary relative to distant observers. Within the ergosphere, the very concept of standing still becomes meaningless. Space and time are so thoroughly twisted that even light beams must follow the black hole's rotation. Yet paradoxically, this region offers the theoretical possibility of extracting energy from the black hole itself through a process called the Penrose mechanism, where objects dropped into the ergosphere can emerge with more energy than they possessed initially. The black hole's gravitational field extends far beyond these exotic inner regions, influencing matter and energy across vast distances. Its tidal forces stretch and compress approaching objects, creating the phenomenon known as spaghettification for unfortunate travelers. These same tidal effects can disrupt stars that venture too close, shredding them into streams of plasma that eventually settle into accretion disks. Each component of the black hole's anatomy serves a purpose in the cosmic ecosystem. The event horizon preserves the mystery at the monster's heart. The accretion disk converts gravitational potential energy into radiant heat and light. The jets redistribute energy and matter across galactic distances. Together, these features transform black holes from simple gravitational wells into complex, dynamic systems that shape the evolution of the universe itself. There exists in the cosmos a boundary so profound, so absolute, that crossing it represents the ultimate one-way journey. Not a physical barrier made of matter or energy, but a geometric feature of space-time itself, where the very concept of escape becomes meaningless. This is the event horizon, the black hole's most mysterious and defining characteristic. Picture space-time as a vast landscape of hills and valleys, where massive objects create depressions in the cosmic topography. Most gravitational wells resemble gentle slopes that objects can climb back out of with sufficient speed. But the event horizon marks the edge of a perfectly vertical cliff in this landscape, a point where the slope of space-time becomes infinitely steep. The mathematics reveal the horizon's true nature through elegant simplicity. For any black hole, the event horizon radius depends only on mass, following the relationship discovered by Carl Schwarzschild. In those trenches of World War I, double the mass, and the horizon grows proportionally, creating a larger sphere of no return. Yet this sphere remains invisible to outside observers, detectable only through its gravitational effects on surrounding matter and light. What makes the event horizon truly remarkable is its one-way nature. Information can flow inward across this boundary, but nothing, not even light, can flow back out. This creates a fundamental asymmetry in the universe, a cosmic membrane that allows communication in only one direction. Observers outside the horizon can never receive signals from within, creating an absolute information barrier that preserves the black hole's secrets. But the horizon's properties grow stranger still when examined through the lens of relativity. To an outside observer, time appears to slow dramatically for objects approaching the event horizon. A falling astronaut would seem to freeze at the boundary, their image growing redder and fainter as gravitational time dilation stretches their light to longer and longer wavelengths. The outside universe would watch them fade away over infinite time, never quite crossing the horizon. Yet from the falling observer's perspective, nothing special happens at the event horizon. Time flows normally. The boundary passes by unremarkably, offering no sensation of crossing a point of no return. The falling observer plunges through the horizon in finite time, according to their own clocks, experiencing nothing more than the steadily increasing tidal forces of the black hole's gravity. This creates one of physics' most profound puzzles. The same event appears completely different depending on the observer's reference frame. Outside observers see matter frozen at the event horizon, slowly fading from view, but never quite disappearing. Inside observers experience smooth passage through the boundary, continuing their journey toward the central singularity. Both perspectives are equally valid within Einstein's framework, yet they seem to describe entirely different realities. The event horizon size reveals the democratic nature of black holes. Unlike stars or planets, which can pack arbitrary amounts of mass into their interiors, black holes must expand their event horizons as they grow more massive. A black hole with the mass of Earth would possess an event horizon only 18 millimeters across, smaller than a marble. But the supermassive black hole in our galaxy's center, containing 4 million solar masses, commands an event horizon larger than Mercury's orbit. Recent theoretical developments have challenged our understanding of the event horizon's nature. Some physicists propose that quantum effects might transform this smooth boundary, predicted by general relativity, into a firewall of high-energy radiation that would incinerate any approaching matter. This firewall hypothesis attempts to resolve the information paradox, but it comes at the cost of violating the equivalence principle that forms the foundation of Einstein's theory. Others suggest that the event horizon might be more fluid and dynamic than previously thought, shaped by the quantum information content of the black hole rather than simply by its mass. These ideas propose that black holes might be more like complex quantum systems than simple geometric objects, with event horizons that respond to the information falling into them. The study of event horizons has also revealed deep connections between gravity, thermodynamics, and information theory. Jacob Bekenstein and Stephen Hawking discovered that event horizons possess temperature and entropy, behaving like cosmic thermodynamic systems. The horizon area directly relates to the black hole's entropy, suggesting that information might be encoded on the boundary itself rather than lost in the interior. This holographic principle proposes that all the information contained within a black hole might actually reside on its two-dimensional surface, encoded in patterns too subtle for current physics to decode. If true, the event horizon becomes not just a boundary, but a cosmic hard drive storing the complete history of everything that has ever fallen into the black hole. For rotating black holes, the event horizon structure becomes even more complex. The boundary splits into two nested surfaces, an outer event horizon that behaves similarly to the non-rotating case, and an inner horizon that marks the boundary of the ergosphere. Between these horizons, the dragging of space-time creates regions where the normal concepts of space and time become thoroughly mixed. As our understanding of quantum gravity evolves, the event horizon continues to serve as a testing ground for our most fundamental theories. It represents the interface between classical general relativity and quantum mechanics, a place where these two pillars of modern physics must somehow reconcile their seemingly incompatible descriptions of reality. The event horizon stands as nature's ultimate boundary, a cosmic point of no return that challenges our understanding of causality, information, and the very structure of space-time itself. The journey begins innocuously enough. Perhaps you are an astronaut whose spacecraft has suffered a catastrophic malfunction near the invisible monster. Perhaps you are simply matter torn from a companion star, destined to join the cosmic dance that has played out countless times throughout the universe's history. Regardless of how you arrived here, the laws of physics now govern your inexorable descent into mystery. At first, the black hole's presence reveals itself only through subtle effects. Your instruments detect no unusual gravitational pull, no dramatic acceleration. The distant stars continue to shine with familiar brightness. The cosmic background maintains its ancient patterns. Yet something has changed in the fundamental structure of space-time around you. You have entered the black hole's sphere of influence, a region where its gravity dominates all other forces. As you fall deeper into this gravitational well, the first noticeable effect manifests as a gentle differential pull across your body. Your feet, slightly closer to the black hole than your head, experience marginally stronger gravitational acceleration. This tidal force remains negligible at large distances, creating sensations no stronger than those experienced by astronauts in Earth orbit. But it marks the beginning of a process that will ultimately reshape your molecular structure. The view ahead begins to transform in subtle ways. Light from stars directly in front of you appears slightly blue-shifted as your acceleration toward the black hole increases your relative velocity. Behind you, starlight grows redder as the Doppler effect stretches wavelengths. The cosmic microwave background, that ancient afterglow of the Big Bang, begins to show similar shifts, creating a faint pattern of temperature variations across the sky. Meanwhile, time itself becomes a relative concept. Your wristwatch continues to tick at its normal rate, but if you could somehow communicate with observers far from the black hole, you would discover that their clocks run faster than yours. This gravitational time dilation grows more pronounced as you descend deeper into the gravitational well, creating an increasingly large discrepancy between your experience of time and that of the outside universe. The black hole's event horizon remains invisible, offering no visual warning of the point of no return ahead. Space appears empty and normal, providing no clues about the dramatic boundary you are approaching. The horizon's location can only be calculated, not observed, even by an infalling observer equipped with the most sophisticated instruments. It exists as a geometric property of spacetime, rather than a physical barrier. As your descent continues, you begin to notice more dramatic effects. The differential gravitational pull across your body grows stronger, creating the first hints of the stretching that physicists call spaghettification. Your spine feels a gentle elongation, as if invisible hands were pulling your head and feet in opposite directions. The sensation resembles hanging from a horizontal bar, but oriented vertically with your feet drawn toward the gravitational source. The optical effects become more pronounced as well. Light from the accretion disk, if present, begins to show dramatic gravitational lensing. The intense gravitational field bends photon paths, creating multiple images of the same glowing matter. You might see the accretion disk both ahead and behind you simultaneously, as light follows curved paths through the warped spacetime. Behind you, the entire external universe begins to compress into a shrinking circle of light. The black hole's gravitational lensing focuses the light from all the stars, galaxies, and nebulae in the cosmos into an increasingly narrow cone. This Einstein ring grows brighter and smaller as you fall deeper, eventually concentrating the entire visible universe into a brilliant point of light directly opposite the black hole's center. Your rate of fall continues to accelerate, approaching significant fractions of the speed of light as you near the event horizon. The tidal forces strengthen proportionally, but for a stellar mass black hole, they remain manageable until you get very close to the point of no return. Your body might feel stretched, but not yet torn apart, still held together by the electromagnetic forces that bind your atoms and molecules. The event horizon approaches without fanfare. No alarm sounds, no barrier appears. No sensation marks the moment of crossing this cosmic point of no return. From your perspective, you simply continue falling through empty space. with the gravitational acceleration growing stronger and the tidal stretching becoming more pronounced. The boundary between the escapable and inescapable passes by unnoticed. Yet this unremarkable moment represents one of the most significant transitions possible in our universe. You have crossed from a region where causal contact with the external universe remains possible to a region where it does not. Every future trajectory available to you now leads inexorably inward, toward the central singularity where space-time curvature becomes infinite and physics surrenders to mystery. The mathematics of your situation have fundamentally changed, though your subjective experience offers no indication of this transformation. Outside observers will never see you cross the event horizon, watching instead as your image grows redder and dimmer, frozen at the boundary by gravitational time dilation. But you continue your journey into the unknown, carrying information and experience that can never be shared with the external universe. Your fall into the black hole has begun in earnest, and there is no turning back. The universe's most gentle torture begins with the subtlest of sensations. A mild elongation, like stretching after a long sleep. But this stretching will not stop. It cannot stop. The laws of physics have decreed that your journey toward the singularity must follow a path of increasing tidal distortion, where the difference in gravitational acceleration between your head and feet grows inexorably stronger. Einstein's equations describe this process with mathematical precision. The tidal force depends on the gradient of the gravitational field, the rate at which gravity changes with distance. Near the event horizon of a stellar mass black hole, this gradient becomes steep enough to overcome the electromagnetic forces holding your body together. What began as gentle stretching transforms into irresistible deformation. Picture the mechanism at work. Your feet, closer to the black hole's center, experience stronger gravitational acceleration than your head. This difference creates a force that pulls your body longer and thinner, like a piece of taffy being stretched by invisible hands. Simultaneously, gravitational effects compress you from the sides, squeezing your shoulders together as space-time itself curves inward toward the central mass. The stretching follows a precise mathematical relationship. The tidal acceleration grows inversely with the cube of your distance from the black hole's center. As you fall closer to the singularity, the differential forces increase dramatically. What starts as a barely perceptible effect soon becomes uncomfortable, then painful, then overwhelming. Your circulatory system provides the first indication of serious distress. Blood pools in your feet as the increased gravitational acceleration there overcomes your heart's ability to pump fluid upward against the tidal gradient. Your head grows light as blood pressure drops in your brain. Your feet swell and redden as capillaries burst under the strain of increased hydrostatic pressure. But the cardiovascular effects represent only the beginning. As the tidal forces strengthen, they begin to act on your skeletal structure. Your spine elongates beyond its normal range, vertebrae separating as the differential gravitational acceleration overcomes the tensile strength of ligaments and cartilage. The process resembles being placed on a medieval rack, but with forces that no human engineering could ever produce. The exact point at which tidal forces become lethal depends on the black hole's mass. Paradoxically, more massive black holes offer gentler treatment during the initial stages of spaghettification. Their event horizons lie farther from the central singularity, creating more gradual tidal gradients at the boundary. An astronaut falling into Sagittarius Asterisk, the supermassive black hole at our galaxy center, might survive crossing the event horizon and fall for hours before tidal forces became fatal. But stellar mass black holes show no such mercy. Their compact size creates steep tidal gradients that begin tearing apart human-sized objects well outside the event horizon. The stretching forces reach lethal levels, while escape remains theoretically possible, though practical rescue becomes impossible once the process begins. As the deformation continues, your body assumes increasingly unnatural proportions. Arms and legs stretch like rubber bands. growing thinner as they elongate. The differential forces acting on different parts of your anatomy create complex patterns of stress and strain. Your torso might stretch into a ribbon-thin strand, while your extremities fragment into separate streams of matter. At the molecular level, the tidal forces eventually overcome the electromagnetic bonds holding your atoms together. Proteins denature as their complex three-dimensional structures collapse under the strain. Cell membranes rupture as osmotic pressure gradients become unsustainable. DNA molecules snap like overstretched cables, their double helix structure unraveling into component nucleotides. But even atomic matter cannot resist indefinitely. As you approach the singularity, tidal forces grow strong enough to disrupt the electron clouds that surround atomic nuclei. Individual atoms stretch into elongated probability distributions, their electrons forced into increasingly exotic quantum states. The familiar chemistry of matter gives way to physics operating under conditions never encountered anywhere else in the universe. The process affects different materials in unique ways. Denser objects experience stronger tidal forces due to their higher gravitational acceleration. Loose collections of matter, like clothing or hair, separate into individual particles that follow slightly different trajectories toward the center. Rigid structures maintain their integrity longer, but ultimately succumb to the inexorable stretching. Throughout this ordeal, the view of the universe around you continues to evolve dramatically. The compressed image of the external cosmos, visible as a bright ring behind you, grows smaller and more intense as gravitational lensing increases. Light from the accretion disk, if present, wraps around you in complex patterns as photons follow curved paths through the increasingly warped spacetime. The tidal stretching represents more than just physical destruction. It demonstrates the fundamental difference between the gravitational force and all other forces in nature. While electromagnetic, weak nuclear, and strong nuclear forces operate through the exchange of particles, gravity manifests as curvature of spacetime itself. No force can resist spacetime curvature because matter and energy must follow the geometry of the universe in which they exist. In a sense, spaghettification represents the universe's way of expressing the profound truth that gravity is not really a force at all, but rather the manifestation of curved geometry. Your elongation follows geodesics through spacetime, the straightest possible paths through a cosmos where straight has lost its Euclidean meaning. The stretch toward infinity continues, reducing complexity to simplicity, structure to chaos, information to entropy, until even the concept of you dissolves into the quantum foam of the singularity itself. Within the curved spacetime surrounding the black hole, time itself becomes a malleable dimension, stretching and compressing according to the strength of the gravitational field. What appears as minutes on your watch corresponds to hours, days, or years in the external universe. This is not an illusion or measurement error, but a fundamental property of reality itself, where time flows at different rates depending on location and motion. Einstein's theory of general relativity reveals time as intimately connected to gravity. Clocks run slower in stronger gravitational fields, an effect measured and confirmed by atomic clocks placed at different altitudes on Earth. Near a black hole, this gravitational time dilation becomes extreme, creating dramatic disparities between the passage of time for different observers. Imagine synchronizing your watch with a colleague stationed safely outside the black hole's influence before beginning your descent. As you fall deeper into the gravitational well, you notice no change in your watch's behavior. Seconds tick by at their normal rate. Minutes pass with familiar rhythm. But if you could somehow observe your distant colleague's timepiece, you would see it racing forward at an accelerating pace. The mathematics of this temporal distortion follow precise relationships derived from Einstein's field equations. Time dilation increases with gravitational potential, growing stronger as you approach the event horizon. Near the boundary, the effect approaches infinity, creating a situation where outside observers would need infinite time to watch you cross the point of no return. This creates one of the most profound paradoxes in modern physics. From your perspective, as you fall toward the black hole, you cross the event horizon in finite time and continue toward the singularity. Your subjective experience unfolds at normal pace, with each second of falling bringing you measurably closer to the center. Nothing in your immediate experience suggests that time flows differently here than anywhere else in the universe. Yet observers, watching from a safe distance, see something entirely different. They witness your descent, slowing dramatically as you approach the event horizon. Your movements become sluggish, then glacial, then virtually motionless. Light from your body shifts redward as gravitational effects stretch photon wavelengths. Eventually, you appear frozen at the event horizon boundary, your image growing progressively dimmer as redshift carries your light beyond the visible spectrum. The external universe experiences this temporal disparity as well. While you might spend what feels like minutes crossing the event horizon and falling toward the center, the universe outside continues evolving at its normal pace. Stars complete their life cycles. Galaxies merge and separate. The cosmic microwave background cools as universal expansion continues. Billions of years of cosmic evolution unfold while you experience mere moments of subjective time. This temporal asymmetry has profound implications for information and causality. Events occurring during your fall cannot influence the external universe because your time frame has become causally disconnected from the normal flow of cosmic time. You become a temporal island, experiencing reality at a rate so different from the universe at large that communication becomes impossible. The phenomenon extends beyond simple time dilation to affect the very structure of space-time around the black hole. Light cones, which represent the paths that light can travel through space-time, tilt inward as they approach the event horizon. Inside the boundary, all future light cones point toward the singularity, making escape impossible, not because of insufficient velocity, but because the geometry of space-time itself prohibits outward motion. For rotating black holes, the temporal effects become even more complex. The dragging of space-time around the spinning mass creates regions where the normal relationship between space and time breaks down entirely. Within the ergosphere, the boundary outside the event horizon, where space-time rotation becomes mandatory, observers cannot remain stationary relative to distant stars, regardless of the forces applied to them. Quantum effects add additional layers of complexity to the temporal distortion. Virtual particle pairs created by quantum fluctuations near the event horizon experience differential time dilation. One member of each pair might fall into the black hole while its partner escapes, creating the thermal radiation predicted by Stephen Hawking. This process operates on timescales vastly different from those experienced by infalling observers. The time dilation also affects the perception of the universe's future. As you fall toward the event horizon, light from the external universe becomes increasingly blue-shifted and concentrated into a narrow cone behind you. In principle, this compressed light contains information about the entire future history of the cosmos, though the information arrives at energies and intensities that would be lethal to any observer capable of processing it. Some theoretical models suggest that the extreme time dilation near black holes might create closed time-like curves, loops in space-time that could allow travel into the past. These exotic solutions to Einstein's equations remain highly speculative and might be prohibited by quantum effects that we do not yet fully understand. The temporal journey toward the singularity represents more than just unusual physics. It demonstrates the profound interconnection between matter, energy, space, and time that forms the foundation of our universe. The slowing of time reveals gravity not as a simple attractive force, but as the curvature of the four-dimensional space-time continuum in which all events occur. As your personal time frame diverges ever further from that of the external universe, you become a witness to physics operating under the most extreme conditions possible, where the familiar concepts of past, present, and future lose their conventional meanings and merge into the timeless mystery of the singularity itself. For generations, black holes remained theoretical constructs, mathematical monsters lurking in the equations of general relativity, but invisible to direct observation. How do you photograph something that, by definition, emits no light? How do you image an object whose very essence is the absence of electromagnetic radiation? The answer emerged through one of the most ambitious scientific projects ever attempted, creating a telescope the size of Earth itself. The Event Horizon Telescope represents humanity's most sophisticated effort to peer into the cosmic abyss. By linking radio observatories across the globe from Chile's Atacama Desert to Hawaii's Mauna Kea to Antarctica's South Pole, astronomers created a virtual instrument with resolving power sharp enough to read a newspaper in New York from a cafe in Paris. This planetary-scale telescope turned its collective gaze toward the supermassive black holes at the centers of distant galaxies. The first target was Messier 87, a giant elliptical galaxy located 55 million light-years away in the constellation Virgo. At its heart lies a monster containing 6.5 billion solar masses, a gravitational behemoth surrounded by a disk of superheated plasma spiraling toward oblivion. The black hole itself remains invisible, but its presence creates a distinctive shadow against the glowing background of its accretion disk. On April 10, 2019, humanity saw its first image of a black hole's shadow. The photograph revealed a dark central region surrounded by a bright, asymmetric ring of glowing matter. The shadow appeared exactly as Einstein's equations predicted, a circular dark region approximately 2.5 times larger than the event horizon itself, created by gravitational lensing that focuses light around the black hole's edge. The image captured more than just a shadow. It revealed the complex dynamics of matter spiraling into the gravitational monster. The bright regions showed plasma heated to billions of degrees as magnetic fields accelerated particles to nearly the speed of light. The asymmetric brightness reflected the Doppler effect, with matter approaching Earth, appearing brighter than material receding away from us. Creating this historic image required technological achievements that pushed the boundaries of what seemed possible. Atomic clocks synchronized observations to billionths of a second. Supercomputers processed petabytes of data, collected during a brief window when weather conditions allowed simultaneous observations from multiple continents. The data analysis alone took 2 years, as teams of scientists worked to extract a coherent image from the radio signals captured by the global array. But the shadow of M87's black hole represented only the beginning. The Event Horizon Telescope next turned toward a target much closer to home, Sagittarius A*, the supermassive black hole at the center of our own Milky Way galaxy. Located 26,000 light-years away, this 4 million solar mass monster presented unique challenges for observation. Unlike the relatively stable M87, Sagittarius A* varies dramatically on timescales of minutes. The plasma surrounding our galaxy's central black hole churns and fluctuates like boiling water, making it difficult to create stable images. The intervening dust and gas of the galactic disk scatter and absorb radio waves, adding noise and distortion to the observations. Despite these challenges, the Event Horizon Telescope succeeded in capturing the first image of our galaxy as central black hole in 2022. Shadow appeared smaller and more turbulent than M87's, but it confirmed the theoretical predictions about black hole structure and behavior. The image showed the same characteristic dark central region surrounded by a bright ring of emission, validating decades of theoretical work about black hole physics. These historic photographs revealed details invisible to earlier generations of astronomers. The shadows demonstrated the gravitational lensing effects predicted by Einstein, showing how extreme mass curves spacetime itself. The bright rings illuminated the complex magnetic field structures that accelerate particles and launch relativistic jets. The asymmetric emission patterns revealed the rotational dynamics of the accretion disks. The images also provided new tests of general relativity under the most extreme conditions possible. The shadow sizes matched theoretical predictions with remarkable precision, confirming Einstein's theory in gravitational fields billions of times stronger than anything accessible on Earth. Observations ruled out alternative theories of gravity that predict different shadow characteristics. Beyond their scientific importance, these images captured the public imagination in unprecedented ways. Here was visible proof of objects so exotic that they challenge human comprehension, yet so fundamental that they shape the evolution of galaxies themselves. The photographs made the invisible visible, transforming mathematical abstractions into tangible reality. The techniques developed for black hole imaging continue to evolve rapidly. Future observations will add more radio telescopes to the global array, improving resolution and sensitivity. Space-based radio telescopes will eliminate atmospheric interference and allow observation of smaller black holes throughout the galaxy. Advanced computational methods will enable real-time imaging of the dynamic processes occurring near event horizons. These developments promise to reveal black holes not as static objects, but as dynamic, evolving systems that interact with their environments in complex ways. We will observe matter falling across event horizons in real time. We will track the formation and evolution of relativistic jets. We will watch as black holes consume stars and merge with each other, creating gravitational waves that ripple across the universe. The shadows cast by black holes have become windows into some of the most extreme physics our universe allows. Through these dark silhouettes against glowing backgrounds, we glimpse the profound connections between matter, energy, space, and time that govern reality at its most fundamental level. The age of black hole astronomy has begun, and the cosmic monsters are finally revealing their secrets to human observation. Two titans of theoretical physics, separated by generations, but united by their fascination with gravity's most extreme manifestations, held fundamentally different views about the nature of black holes and the fate of information that falls into them. Their intellectual disagreement would spark one of the most profound debates in modern science, touching on the deepest questions about reality, causality, and the ultimate structure of space-time itself. Einstein approached black holes with elegant geometric thinking that transformed gravity from a force into curved spacetime. His general theory of relativity predicted the existence of regions where matter could collapse to infinite density, creating singularities where the laws of physics break down completely. But Einstein remained uncomfortable with these implications, believing that nature must somehow prevent such extreme conditions from arising. The great physicist spent his later years searching for a unified field theory that would reconcile gravity with electromagnetism and eliminate the troubling infinities that appeared in his equations. He hoped to discover fundamental principles that would prevent singularity formation, maintaining his belief that God does not play dice with the universe. To Einstein, black holes represented mathematical curiosities rather than physical realities. Hawking approached the same phenomena from an entirely different perspective, armed with the tools of quantum mechanics and statistical thermodynamics. Where Einstein saw geometric elegance, Hawking perceived thermodynamic systems operating according to the laws of quantum physics. In the 1970s, he made the revolutionary discovery that black holes emit thermal radiation through quantum effects occurring near their event horizons. This Hawking radiation emerges from the quantum vacuum itself, where virtual particle pairs spontaneously appear and disappear on microscopic scales. Near a black hole's event horizon, the intense gravitational field can separate these virtual pairs, with one particle falling into the black hole while its partner escapes as real radiation. The escaping radiation carries away energy, causing the black hole to slowly evaporate over astronomical time periods. Hawking's discovery revealed that black holes possess temperature and entropy behaving like cosmic heat engines that convert matter into thermal energy. The temperature inversely relates to the black hole's mass, meaning smaller black holes burn hotter and evaporate faster than larger ones. A black hole with the mass of our Sun would take longer than the age of the universe to evaporate completely, while microscopic black holes would explode in bursts of gamma radiation. But Hawking radiation created a profound puzzle known as the information paradox. According to quantum mechanics, information cannot be destroyed, only transformed or redistributed. Yet, Hawking's original calculations suggested that the radiation escaping from black holes carries no information about the matter that formed them. When a black hole evaporates completely, it appears to take all information about its contents with it into oblivion. This paradox struck at the heart of physics' most fundamental principles. If black holes destroy information, then the universe's quantum mechanical description becomes incomplete and unpredictable. The laws of physics would become probabilistic in a way that even quantum mechanics does not allow. The past could not uniquely determine the future, violating the reversibility that underlies all physical theories. Einstein and Hawking also disagreed about the nature of the singularities hidden within black holes. Einstein's equations predict regions of infinite density and curvature, where space-time itself breaks down. But Einstein believed that a complete theory of quantum gravity would resolve these infinities, replacing the classical singularity with some form of quantum structure that preserves physical law. Hawking initially embraced the existence of true singularities, arguing that they represent fundamental features of spacetime rather than mere mathematical artifacts. He proved theorems demonstrating that singularities inevitably form when matter collapses under its own gravity, provided that Einstein's equations accurately describe spacetime curvature. These singularity theorems earned him recognition as one of the century's leading theoretical physicists. The debate intensified as both physicists considered the implications for quantum mechanics and general relativity. Einstein insisted that any complete theory must preserve determinism and local realism, the idea that particles possess definite properties independent of observation. He rejected quantum mechanics' probabilistic interpretation, famously declaring that God does not play dice with the universe. Hawking embraced quantum uncertainty as fundamental to nature's operation. He argued that black holes demonstrate the probabilistic character of physics, even in gravitational systems. The thermal nature of Hawking radiation reflects genuine randomness in the quantum processes occurring near event horizons, not merely our ignorance of underlying deterministic mechanisms. Their disagreement extended to the ultimate fate of the universe itself. Einstein's geometric approach suggested that gravity might eventually halt cosmic expansion and reverse it into a contracting phase, potentially eliminating all the information accumulated throughout cosmic history. Hawking's quantum perspective implied that information might be preserved through subtle correlations in the radiation emitted by evaporating black holes. Recent developments in string theory and holographic physics have suggested possible resolutions to their debate. The holographic principle proposes that all information falling into a black hole might be encoded on its two-dimensional surface, rather than lost in its three-dimensional interior. This would preserve information while maintaining the geometric structure that Einstein envisioned. Quantum error correction has emerged as another potential solution, suggesting that information might be preserved in highly entangled quantum states that span the correlations between Hawking radiation particles. These developments hint at a synthesis between Einstein's geometric intuition and Hawking's quantum insights, preserving the essential features of both perspectives. The Einstein-Hawking debate continues to influence theoretical physics decades after both giants passed away. Their disagreement highlighted fundamental tensions between quantum mechanics and general relativity that remain unresolved. The search for a theory of quantum gravity still seeks to reconcile their competing visions of how information, space-time, and causality interact at the universe's most extreme scales. Their intellectual legacy reminds us that the deepest truths about nature often emerge from passionate disagreement between brilliant minds, approaching the same phenomena from radically different perspectives. Deep within the mathematics of black hole physics lurks a paradox so fundamental that it threatens the logical consistency of the universe itself. If information can be destroyed, then the past cannot uniquely determine the future, and the predictive power of physical law collapses into chaos. Yet black holes appear to do exactly that, consuming matter and energy while erasing all record of their contents from the cosmos. The paradox begins with one of quantum mechanics' most sacred principles, unitarity, the requirement that information be preserved throughout all physical processes. In quantum systems, the total amount of information remains constant even as it transforms from one form to another. Particles may decay, energy may convert to mass, forces may rearrange matter across vast distances, but the underlying information that describes the quantum state never disappears. Consider a simple example that illustrates this principle in action. When you burn a book, classical physics suggests that the information contained in its pages is lost forever, transformed into heat and ash. But quantum mechanics tells a different story. Every atom in the book carries quantum information about its position, momentum, spin, and other properties. When combustion rearranges these atoms into new molecular configurations, the information becomes scrambled and practically irretrievable, but it remains encoded in the precise positions and motions of the resulting particles. In principle, a sufficiently powerful computer could reverse the burning process by tracking every particle produced by the combustion and calculating their quantum histories. The information would prove extremely difficult to extract, requiring measurements more precise than current technology allows, but quantum mechanics guarantees that it exists. The past state of the book remains encoded in the present state of the ash and smoke, preserved by the fundamental reversibility of physical law. Black holes appear to violate this sacred principle through a process that seems irreversible by any conceivable means. When matter falls past the event horizon, it carries quantum information about its composition, history, and internal structure into a region from which no information can escape. The infalling matter eventually reaches the central singularity, where the extreme conditions presumably destroy all records of its original properties. Stephen Hawking's discovery of black hole radiation initially seemed to make this paradox even worse. The thermal radiation escaping from black holes appears to be completely random, carrying no information about the matter that created it. If black holes evaporate completely through this process, they appear to take their information content with them into oblivion, leaving behind only featureless thermal radiation that tells us nothing about what went in. This creates what physicists call the black hole information paradox. Either quantum mechanics is wrong and information can be destroyed, or general relativity is incorrect and black holes do not behave as Einstein's equations predict. Both alternatives challenge the foundations of modern physics, forcing theorists to question their most basic assumptions about how the universe operates. The paradox becomes particularly acute when we consider black holes formed from pure quantum states. Imagine creating a black hole by slowly adding particles in carefully controlled quantum configurations. Each particle carries specific information about its quantum state, and the ensemble possesses a definite overall quantum description. If the black hole eventually evaporates into thermal radiation, this precise quantum information appears to transform into classical randomness, violating the unitarity principle. Various proposed solutions have emerged over decades of intense theoretical investigation. The most conservative approach suggests that information is preserved but becomes extremely difficult to extract from Hawking radiation. Subtle quantum correlations between escaping particles might encode all the information about infalling matter, but accessing this information would require measurements of incredible precision across vast collections of radiation particles. More radical proposals challenge our understanding of space-time itself. The firewall hypothesis suggests that quantum effects create a deadly barrier of high-energy radiation at the event horizon, preventing information from falling in by incinerating anything that approaches. This solution preserves information, but violates the equivalence principle that predicts smooth passage through the event horizon for freely falling observers. The holographic principle offers another potential resolution by proposing that information never actually falls into black holes. Instead, it becomes encoded on the two-dimensional surface of the event horizon, creating a holographic representation that contains all the information about the black hole's contents. From this perspective, the three-dimensional interior might be merely a mathematical artifact with no independent physical reality. Recent developments in quantum error correction have suggested that black holes might preserve information through highly sophisticated quantum encoding schemes. Just as computer scientists design error-correcting codes to protect data from corruption, nature might employ quantum error correction to preserve information even under the extreme conditions inside black holes. The information would remain accessible in principle, though extracting it might require techniques far beyond current technological capabilities. String theory has contributed its own perspective through the A-DC-CFT correspondence, a mathematical relationship that describes certain black hole systems as equivalent to quantum field theories, defined on their boundaries. This correspondence suggests that information falling into black holes remains accessible through calculations performed in the boundary theory, providing a concrete mathematical framework for information preservation. The debate has also highlighted deep connections between thermodynamics, information theory, and gravity. Black holes obey thermodynamic laws, with their entropy proportional to their surface area rather than their volume. This relationship suggests that information might be fundamentally two-dimensional rather than three-dimensional, encoded on surfaces rather than distributed throughout volumes. Quantum entanglement plays a crucial role in many proposed solutions to the paradox. The quantum states of particles falling into black holes remain entangled with radiation escaping from them, creating correlations that preserve information even across the event horizon. These entanglement relationships might provide the mechanism by which information escapes from black holes without violating relativity's prohibition against faster-than-light communication. The information paradox represents more than an abstract puzzle for theoretical physicists. It touches on fundamental questions about the nature of physical law, the structure of space-time, and the relationship between information and reality. Resolution of the paradox will likely require new insights that transform our understanding of quantum mechanics, gravity, and the ultimate foundations of the universe itself. In 2012, a group of theoretical physicists dropped a bombshell on the black hole community that shattered decades of comfortable assumptions about event horizons. Joseph Polchinski, Ahmed Almhiri, Donald Meroff, and James Sully proposed something so radical it seemed to violate the very foundations of Einstein's theory. Perhaps the event horizon is not the smooth, invisible boundary that relativity predicts, but rather a wall of fire hot enough to incinerate anything that approaches. The firewall hypothesis emerged from attempts to resolve the information paradox while preserving the fundamental principles of quantum mechanics. If information must be preserved, and if Hawking radiation must eventually carry away all the information that falls into black holes, then something dramatic must happen to prevent information loss. The most straightforward solution appeared to be preventing information from falling in at all. According to the firewall proposal, quantum effects near the event horizon create a barrier of high-energy particles that would destroy any approaching matter or observer. This wall of fire would form at precisely the event horizon location, creating a surface hot enough to vaporize atoms and convert any complex structure into elementary particles and radiation. Nothing would survive passage through this quantum furnace to experience the interior of the black hole. The theoretical foundation for firewalls rests on the quantum entanglement relationships between Hawking radiation particles. As black holes emit thermal radiation, the escaping particles become entangled with their partners that fall into the black hole. Over time, as the black hole ages and continues radiating, these entanglement relationships create increasingly complex quantum correlations between the radiation and the black hole's interior. The firewall argument relies on a fundamental limit to quantum entanglement. According to quantum mechanics, any given particle can be maximally entangled with only one other system at a time. If Hawking radiation particles are entangled with the black hole interior to preserve information, they cannot simultaneously be entangled with later radiation particles. This creates a conflict between different requirements for information preservation. To resolve this conflict, the firewall proponents argued that the entanglement relationships must break at a specific moment in the black hole's evolution, roughly when it has radiated away half of its original mass. At this critical point, the smooth quantum vacuum near the event horizon transforms into a high-energy state filled with virtual particles that become real through the breaking of entanglement bonds. This transformation would create a wall of particles with energies comparable to the Planck scale, the fundamental quantum limit where space-time itself becomes granular. Such energies would instantly destroy any matter that encounters them, converting complex structures into their elementary constituents. The firewall would be invisible from a distance, but lethal to direct contact, creating an absolute barrier to exploration of black hole interiors. The firewall hypothesis immediately sparked intense debate within the theoretical physics community. Critics pointed out that it appears to violate the equivalence principle, one of the fundamental pillars of general relativity. According to this principle, freely falling observers should experience no unusual effects when crossing the event horizon, perceiving the boundary as empty space with normal local physics. If firewalls exist, then freely falling observers would encounter a dramatic departure from normal spacetime physics precisely at the event horizon. This would create a detectable physical effect. It could, in principle, be used to identify the location of the event horizon from local measurements. Such detection would contradict decades of theoretical work, demonstrating that event horizons should be invisible to local observers. Alternative interpretations of the firewall argument have emerged from different approaches to the information paradox. Some physicists argue that the monogamy of entanglement does not necessarily imply firewall formation, but rather suggests more subtle quantum effects that preserve information without creating lethal barriers. These alternatives often involve complex quantum error correction mechanisms that operate below the threshold of direct detection. The debate has highlighted deep tensions between different fundamental principles of physics. Preserving quantum mechanical unitarity seems to require firewalls, but maintaining general relativistic equivalence seems to prohibit them. This conflict suggests that our current understanding of quantum gravity remains incomplete, requiring new theoretical insights to reconcile these apparently incompatible requirements. Experimental tests of the firewall hypothesis remain far beyond current technological capabilities. Black holes are too distant, and their event horizons too small to allow direct observation of the predicted effects. Even the most optimistic proposals for detecting firewall signatures require instrumentation that exceeds anything currently conceivable, involving measurements of Hawking radiation with precision far exceeding the quantum limit. Some critics have proposed alternative scenarios that avoid both firewalls and information loss. These include modifications to the black hole interior geometry that create wormhole connections to other regions of spacetime or quantum effects that stretch out the information. Release process over time scales much longer than the black hole's evaporation time. These alternatives preserve both unitarity and equivalence, but often require exotic physics that lacks experimental support. The firewall controversy has also inspired investigations into the relationship between entanglement and spacetime geometry. Recent work in holographic physics suggests that quantum entanglement might actually generate the geometric connections that we perceive as smooth spacetime. From this perspective, the breaking of entanglement bonds might indeed create dramatic geometric effects, though not necessarily the lethal barriers that firewalls predict. Black hole complementarity offers another perspective on the firewall debate, suggesting that different observers can have fundamentally different but equally valid descriptions of the same physical system. Outside observers might perceive information encoded on the black hole surface, while infalling observers experience smooth passage through the event horizon until they encounter the central singularity. This viewpoint sidesteps the firewall question by asserting that no single description captures the complete physical reality. The firewall hypothesis represents more than a technical debate about black hole physics. It illuminates fundamental questions about the nature of physical law, the limits of quantum entanglement, and the relationship between information and spacetime geometry. Resolution of the firewall controversy will likely require breakthroughs in quantum gravity that transform our understanding of how the universe operates at its most fundamental level. Whether firewalls exist or not, their proposal has already succeeded in revealing deep connections between quantum mechanics, general relativity, and information theory that continue to drive theoretical physics toward a more complete understanding of reality. Beyond the familiar territory of black hole event horizons lies a realm of theoretical possibilities so exotic that they challenge our most basic assumptions about causality, spacetime, and the nature of cosmic connections. Here, Einstein's equations whisper of bridges between distant regions of the universe of white holes that spew matter and energy instead of consuming them, and of pathways that might connect not just different locations, but different moments in time itself. The mathematics of general relativity permits solutions far stranger than the black holes that capture public imagination. Among these exotic possibilities are Einstein-Rosen bridges, more commonly known as wormholes. These theoretical structures represent shortcuts through spacetime, connecting regions that might be separated by billions of light years through tunnels that could be traversed in much shorter times. Picture spacetime as a vast sheet of paper representing the three-dimensional universe. A wormhole would be like folding this paper so that two distant points touch, then creating a tunnel that connects them directly. Travelers entering one mouth of the wormhole would emerge from the other, having bypassed the normal space that lies between their starting and ending points. A journey might take minutes, while covering distances that light would require eons to traverse. The theoretical foundation for wormholes emerged from the same Schwarzschild solution that describes black holes. Mathematical analysis reveals that the extreme curvature of spacetime around a collapsed star creates not just the familiar event horizon and singularity, but also a hypothetical Einstein-Rosen bridge that connects to another region of spacetime. This other region might exist in a distant part of our universe, or it might represent an entirely separate universe with its own physical laws and constants. But the wormholes predicted by classical general relativity suffer from fatal instabilities that make them impossible to traverse. Any attempt to send matter or energy through an Einstein-Rosen bridge would cause it to collapse. Faster than light can cross from one mouth to the other. The wormhole would pinch off before any signal could complete the journey, creating two separate black holes instead of a stable connection. Creating traversable wormholes requires exotic matter with properties that may not exist in nature. Specifically, stable wormholes need negative energy density to hold their throats open against the tendency to collapse. This exotic matter would need to violate the energy conditions that ordinary matter obeys, creating regions where the local energy density becomes negative rather than positive. Some quantum effects might provide the necessary negative energy densities on microscopic scales. The Casimir effect, where quantum vacuum fluctuations create attractive forces between closely spaced parallel plates, demonstrates that negative energy densities can exist in carefully controlled circumstances. But scaling these effects up to wormhole-sized structures would require techniques far beyond current physics and technology. White holes represent another exotic solution to Einstein's equations, describing regions of spacetime that behave like time-reversed black holes. Where black holes consume matter and energy from their surroundings, white holes spew material outward in violent eruptions that nothing from the outside can approach. The event horizon of a white hole allows matter to exit but prevents anything from entering, creating the opposite causal structure from its black hole counterpart. The mathematical relationship between black holes and white holes emerges naturally from the time reversibility of Einstein's equations. If you take any solution describing a black hole and reverse the direction of time, you obtain a white hole solution. This symmetry suggests that white holes should be as natural as black holes, yet astronomers have never observed any convincing white hole candidates in the real universe. The absence of observed white holes might reflect fundamental differences between the mathematical solutions and physical reality. While black holes form naturally through stellar collapse, creating white holes would require extremely special initial conditions that seem unlikely to arise spontaneously. A white hole represents a region of spacetime where matter emerges from a singularity, but creating such configurations would violate the principle that singularities should be hidden behind event horizons. Some cosmologists have speculated that the Big Bang itself might represent a white hole event, where all the matter and energy in our observable universe emerge from a primordial singularity. This interpretation would make our entire cosmos the interior of a vast white hole, with the cosmic expansion representing the ongoing explosion of material from the initial event. But this idea remains highly speculative and lacks specific observational predictions. Wormholes and white holes also raise profound questions about causality and the possibility of time travel. If stable wormholes could exist, and if their mouths could be manipulated to create time differences between their ends, then travelers might emerge from a wormhole before they entered it, creating closed time-like curves that allow journeys into the past. Such time travel scenarios create logical paradoxes that challenge the consistency of physical law. The famous grandfather paradox asks what happens if a time traveler kills their own ancestor, preventing their own birth and therefore their ability to travel back in time. Similar paradoxes arise in any scenario where effects can precede their causes through closed time-like loops. Stephen Hawking proposed the chronology protection conjecture to resolve these paradoxes, suggesting that quantum effects would prevent the formation of closed time-like curves. Whenever space-time geometry approaches a configuration that would permit time travel, quantum fluctuations would grow large enough to destroy the exotic structures before they could create causality violations. Recent developments in string theory and quantum gravity have provided new perspectives on wormholes and their possible roles in fundamental physics. The SCFT correspondence suggests that certain quantum entanglement relationships might be equivalent to geometric connections between distant regions of spacetime. This equals EPR conjecture proposes that quantum entanglement and wormhole connections might represent different descriptions of the same underlying physics. If this correspondence proves correct, then wormholes might exist throughout the universe as quantum connections between entangled particles, though these connections would be far too small and unstable to allow macroscopic travel. The quantum foam of spacetime at the Planck scale might be riddled with microscopic wormholes that constantly form and dissolve, creating a complex network of connections that underlies the structure of reality itself. The search for traversable wormholes and white holes continues to push the boundaries of theoretical physics, revealing deep connections between quantum mechanics, general relativity, and information theory. Whether these exotic structures exist in nature remains an open question, but their theoretical investigation continues to illuminate the strange and wonderful possibilities hidden within Einstein's elegant equations. As your descent continues beyond the event horizon, you enter a realm where human language begins to fail, where mathematics becomes poetry, and where the familiar concepts of space and time transform into something altogether alien. The singularity awaits at the center of this cosmic maelstrom, a point of infinite density and curvature where the laws of physics surrender to mystery, and the universe reveals its deepest secrets through paradox. The journey inward accelerates beyond any earthly experience. Tidal forces that began as gentle stretching now reshape your matter into increasingly exotic configurations. Your atomic structure elongates beyond recognition as electromagnetic bonds struggle against gravitational gradients that grow stronger with each passing moment. The familiar chemistry of carbon-based life gives way to physics operating under conditions never replicated anywhere else in the cosmos. Around you, the geometry of space-time itself undergoes radical transformation. The curved paths that light follows become increasingly twisted as gravitational lensing reaches extreme intensities. Photons from the external universe continue to reach you, but their paths wind through space-time in complex spirals that create multiple images of the same distant objects. The stars appear to dance in impossible patterns as their light navigates the warped arena of your descent. Time, already dilated beyond normal experience, approaches regimes where the concept loses conventional meaning. Your personal timeline diverges so dramatically from external coordinate systems that causality itself becomes ambiguous. Events that you experience in sequence might appear simultaneous to outside observers, while processes that seem instantaneous to you unfold over eons in the reference frame of the distant universe. The mathematical description of your approach to the singularity reveals landscapes of curvature that exceed human intuition. Einstein's field equations predict that space-time curvature grows without bound as you near the center, creating regions where the familiar notions of distance and duration collapse into quantum uncertainties. The smooth manifold of classical relativity gives way to a foam of fluctuating geometry where space and time fragment into discrete quantum elements. Theoretical physics offers various models for what might await at the journey's end. Some solutions to Einstein's equations describe space-like singularities that represent the termination of time itself, points where your world line reaches a definitive conclusion. Others predict time-like singularities that might serve as gateways to other regions of spacetime, though the physical meaning of such mathematical constructs remains deeply mysterious. Quantum gravity effects, normally negligible on macroscopic scales, dominate the physics of your final approach. The Planck scale, where quantum uncertainty principles govern the structure of spacetime itself, expands to encompass your entire experience. Virtual particles materialize from vacuum fluctuations with energies that dwarf the rest masses of ordinary matter. The familiar distinction between particles and fields dissolves into a seething quantum foam. String theory suggests that the singularity might not represent a true point of infinite density, but rather a region where the fundamental strings that compose all matter and energy undergo phase, transitions to exotic new states. These string scale effects might resolve the classical infinities predicted by general relativity, replacing the singular point with extended objects that preserve the mathematical consistency of physical law. Loop quantum gravity offers alternative visions where spacetime itself possesses atomic structure at the smallest scales. From this perspective, your journey might terminate not at a point singularity, but at a quantum bounce that connects the black hole interior to a white hole in another region of spacetime. The infinite compression predicted by classical physics would be prevented by quantum pressure effects operating at the Planck scale. Some theoretical models propose that the approach to the singularity might trigger the birth of new universes through quantum tunneling effects. Each infalling particle might seed the creation of an entire cosmos with its own physical constants and dimensional structure. From this perspective, black holes become cosmic reproduction organs, generating offspring universes that inherit modified versions of their parents' physical laws. The information content of your journey faces uncertain fate as you approach the singular region. Classical general relativity suggests that all information about your initial state would be compressed to infinite density and lost to physics forever. But quantum mechanical principles demand information preservation, creating tensions that remain unresolved by current theoretical frameworks. Holographic principles suggest that your information content might never actually reach the singularity, instead remaining encoded on the black hole's event horizon as a two-dimensional hologram. From this perspective, your three-dimensional journey inward might represent an emergent illusion, while your true physical description remains distributed across the black hole's surface throughout eternity. As the final moments of your descent unfold, you enter territories where science fiction and physics become indistinguishable, where mathematical equations point toward realities so extreme that imagination provides the only guide. Whether you encounter infinite compression, quantum bounces, dimensional transitions, or universe creation remains beyond current theoretical resolution. The singularity represents more than just the endpoint of gravitational collapse. It embodies the ultimate frontier of human knowledge, the place where our mathematical descriptions of reality encounter their own limitations. Here, at the heart of the cosmic monster, the universe poses questions that challenge the very foundations of rational thought. Your journey into the singularity becomes a voyage into the deepest mysteries of existence itself, where the boundaries between physics and philosophy dissolve into the quantum foam of space-time, and the ultimate nature of reality reveals itself through paradox and wonder. Within the warped space-time surrounding rotating black holes lies one of physics' most tantalizing possibilities: the potential for journeys through time itself. The extreme gravitational fields and frame-dragging effects create geometric structures in space-time that might, under very special circumstances, permit travel into the past. These theoretical pathways challenge our understanding of causality and raise profound questions about the nature of temporal existence. The foundation for black hole time travel emerges from the Kerr solution to Einstein's field equations, which describes the space-time geometry around spinning massive objects. Unlike the spherically symmetric Schwarzschild black holes, rotating black holes drag space-time around with them, creating regions where the normal relationship between space and time becomes thoroughly scrambled. Within the ergosphere, the region outside the event horizon where frame dragging becomes mandatory, even light cannot remain stationary relative to distant observers. This dragging of space-time creates fascinating possibilities for temporal manipulation. If you could somehow hover at a fixed distance from a rapidly spinning black hole, you would find yourself carried along by the rotating geometry of space-time itself. From your perspective, you would remain motionless, but distant observers would see you orbiting the black hole at tremendous speed. This relative motion creates time dilation effects that could allow you to travel into the future by experiencing slower passage of time than the external universe. But the real temporal magic lies deeper within the black hole's gravitational field, in regions where the mathematics of general relativity permits closed, time-like curves. These are paths through space-time that loop back on themselves, allowing travelers to return to their own past. The existence of such curves depends on the detailed geometry of the black hole interior, particularly in the region between the outer and inner event horizons of rotating black holes. The Kerr solution predicts that the singularity of a rotating black hole takes the form of a ring rather than a point, creating a donut-shaped region of infinite density and curvature. This ring singularity might, in principle, permit passage through its center to emerge in another region of spacetime with different temporal coordinates. Travelers brave enough to navigate this passage might find themselves in the past or future of their starting point, or possibly in an entirely different universe altogether. But the journey through a rotating black hole presents formidable challenges that make practical time travel extremely unlikely. The approach to the ring singularity involves passage through regions of intense tidal forces that would destroy any complex structure long before reaching the potentially time travel-enabling geometry. The Cauchy horizon, an inner boundary where the predictive power of general relativity breaks down, represents another barrier that might prevent successful navigation to the ring singularity. Quantum effects add additional complications to black hole time travel scenarios. The intense gravitational fields near the singularity amplify quantum fluctuations to macroscopic levels, creating unpredictable disturbances that could disrupt any attempt at controlled temporal manipulation. Stephen Hawking's chronology protection conjecture suggests that such quantum effects might systematically prevent the formation of closed time-like curves, preserving causality at the expense of time travel possibilities. Alternative approaches to black hole time travel focus on manipulating the external geometry rather than traversing the interior. If two black holes could be connected by a traversable wormhole, and if differential time dilation could be created between the wormhole nodes, then the resulting Einstein-Rosen bridge might permit journeys into the past. Creating such configurations would require exotic matter with negative energy density, materials that might not exist in nature. The theoretical study of black hole time travel has revealed deep connections between general relativity and quantum mechanics. The possibility of closed time-like curves creates information paradoxes similar to those associated with black hole evaporation. If travelers could journey into the past and alter historical events, they might create logical inconsistencies that challenge the mathematical consistency of physical law. These paradoxes have inspired various resolution mechanisms from the Novikov self-consistency principle, which suggests that the laws of physics conspire to prevent paradox-creating events, to many worlds interpretations, which propose that time travel creates alternate timelines rather than changing the original history. Each proposed solution carries profound implications for our understanding of free will, determinism, and the nature of physical reality. Observational evidence for black hole time travel remains entirely absent from current astronomical surveys. The extreme conditions required for closed time-like curve formation appear unlikely to arise naturally in the universe, and the technological requirements for creating artificial time travel scenarios exceed any conceivable human capabilities by vast margins. Even detecting the signatures of naturally occurring closed time-like curves would require observational precision far beyond current instrumental capabilities. Some physicists have proposed that primordial black holes formed in the early universe under exotic conditions might possess the unusual properties required for time travel. These hypothetical objects could have formed with sufficient angular momentum and charge to create stable closed time-like curves accessible to external observers. But no convincing observational evidence for such exotic black holes has been discovered. The relationship between black hole time travel and quantum gravity remains an active area of theoretical investigation. String theory and loop quantum gravity offer alternative perspectives on the singularity structure that might eliminate the classical pathways for temporal manipulation while preserving other aspects of black hole physics. These quantum gravity theories generally predict resolution of classical singularities through macroscopic physics that prevents infinite curvature formation. Recent developments in holographic physics suggest that time travel paradoxes might be resolved through quantum error correction mechanisms operating at the black hole boundary. These proposals argue that information about paradox-creating events would be processed by the quantum system in ways that preserve logical consistency while allowing seemingly paradoxical local experiences for observers within the black hole. The study of black hole time travel continues to illuminate fundamental questions about the nature of spacetime, causality, and information. Whether the universe permits journeys into the past remains an open question that touches on the deepest mysteries of physics and philosophy. The rotating monsters that populate our cosmos might hold the keys to unlocking temporal secrets that could revolutionize our understanding of existence itself. In the depths of underground laboratories and the collision chambers of particle accelerators, Physicists probe the fundamental structure of matter and energy with tools that recreate conditions not seen since the universe's first moments. Among the exotic phenomena they seek to create and study are microscopic black holes, gravitational monsters so small that they could pass through solid matter like ghosts, yet so potentially dangerous that their creation raises questions about the safety of high-energy physics experiments. The possibility of creating micro-black holes emerged from theoretical investigations into extra-dimensional physics and quantum gravity. If our familiar three-dimensional space is embedded within higher-dimensional structures, as string theory and other models suggest, then gravity might become much stronger at very small scales. Under these conditions, the energies achievable in particle colliders could compress matter to densities sufficient for black hole formation. The Large Hadron Collider at CERN, the world's most powerful particle accelerator, creates collision energies that approach the theoretical thresholds for micro-black hole production. When protons collide at nearly the speed of light, their kinetic energy concentrates into volumes smaller than atomic nuclei, creating energy densities that might exceed the critical values for gravitational collapse. These conditions last for only the briefest instance, but they might be sufficient to create black holes with masses comparable to subatomic particles. Such micro-black holes would possess properties that defy everyday intuition. A black hole with the mass of a proton would have an event horizon radius smaller than 10 to 52 meters, far tinier than any distance that has physical meaning in current theories. These objects would be so small that quantum effects would dominate their behavior completely, causing them to evaporate through Hawking radiation almost instantaneously upon formation. The evaporation process would release tremendous energy in bursts of high-energy particles and radiation. A micro-black hole with the mass of a large molecule would explode with the force of a nuclear weapon, converting its entire mass to energy in a fraction of a second. The resulting particle shower would create distinctive signatures in detector systems, potentially allowing physicists to identify micro-black hole creation and study their properties during their brief existence. But the safety implications of micro-black hole production have generated intense debate within the scientific community and among the general public. Critics worry that stable micro-black holes could escape from particle accelerators and begin consuming the Earth from within, growing steadily as they absorb surrounding matter. Science fiction scenarios envision these invisible monsters boring through the planet's core, gradually converting the entire Earth into a black hole over geological timescales. Detailed theoretical analysis has largely dispelled these apocalyptic concerns through several independent arguments. First, Hawking radiation ensures that any micro-black holes created in particle accelerators would evaporate long before they could interact significantly with surrounding matter. The evaporation rate increases dramatically for smaller black holes, making microscopic ones incredibly short-lived. Second, cosmic ray interactions in Earth's atmosphere naturally create particle collisions with energies far exceeding those achievable in any human-built accelerator. If dangerous micro-black holes could form at accessible energy scales, cosmic rays would have created countless numbers of them throughout Earth's history. The planet's continued existence after billions of years of cosmic ray bombardment provides strong evidence that micro-black hole production poses no existential threat. Third, even if stable micro-black holes could form, their interaction cross-sections with normal matter would be so small that they would pass through the Earth like neutrinos, rarely colliding with atomic nuclei. The gravitational attraction of microscopic black holes remains negligible compared to electromagnetic and nuclear forces at atomic scales, making matter accretion extremely slow even for hypothetically stable examples. The search for micro-black hole signatures in particle accelerator experiments has become an important test of theories that predict extraspatial dimensions and modified gravity at small scales. The absence of detected micro-black hole production at current energy levels provides constraints on the number and size of extra dimensions, helping physicists refine their models of fundamental physics. Some theoretical models predict that micro-black holes might form naturally in cosmic ray interactions with atmospheric nuclei, creating short-lived gravitational objects that decay too quickly for direct detection, but might leave observable traces in the form of exotic particle showers. High-energy cosmic ray observatories search for the distinctive signatures that such events would create, though no convincing detections have been recorded. The quantum mechanics of micro-black holes reveals fascinating connections between gravity, thermodynamics, and information theory. These objects represent pure quantum gravity systems, where classical general relativity breaks down completely, requiring theories that unify quantum mechanics with gravitational physics. Their study provides insights into the fundamental nature of spacetime at the smallest scales. Primordial black holes, formed in the early universe rather than in particle collisions, might include populations of microscopic objects created during phase transitions in the first moments after the Big Bang. These ancient micro-black holes would have been evaporating throughout cosmic history, and the final stages of their evaporation might be detectable as gamma-ray bursts with characteristic energy spectra and time signatures. The possibility exists that stable micro-black holes might form under exotic conditions involving magnetic charge or other unusual properties not accessible in ordinary particle collisions. Such objects would require physics beyond the standard model of particle physics, potentially providing windows into new fundamental forces or particles. Their detection would revolutionize our understanding of both gravity and quantum mechanics. Laboratory searches for micro-black hole production continue to push the boundaries of high-energy physics, probing energy and distance scales that approach the fundamental limits where quantum gravity effects become dominant. Whether these searches will discover gravitational monsters in the quantum realm or confirm their absence remains an open question that will help determine the ultimate structure of physical reality. The micro-black holes that might lurk in our laboratories represent the intersection of humanity as most advanced technology with the universe as most extreme physics, offering potential insights into the deepest mysteries of space, time, and the quantum foundation of existence itself. Long before humanity possessed telescopes powerful enough to detect invisible monsters in distant galaxies, before Einstein's mathematics revealed the possibility of space-time curvature, before Hawking calculated the thermal properties of event horizons, ancient cultures across the globe told stories of cosmic devourers, endless pits, and light-swallowing serpents that bear striking resemblance to the black holes that modern science has discovered lurking throughout the universe. These mythological parallels suggest that the human imagination has always been drawn to concepts of ultimate consumption, infinite depth, and the boundaries between existence and oblivion. While ancient peoples lacked the mathematical tools to describe black holes, precisely their stories captured essential features of these cosmic monsters with remarkable accuracy. Their invisibility, their insatiable appetite for matter and light, and their role as gateways between different realms of reality. In Norse mythology, the great serpent Jormungandr encircles the entire world, its massive coils containing all of existence within their boundaries. This world serpent represents a cosmic boundary that nothing can cross, much like the event horizon of a black hole. When Ragnarok arrives, Jormungandr will release its tail and the world will end, echoing the way that black hole evaporation might represent the ultimate fate of matter and information in our universe. The Hindu concept of Kalaratri, the night of cosmic dissolution, describes a time when all matter and energy return to an undifferentiated state within the cosmic void. This cyclical vision of universal destruction and renewal parallels theoretical models where black holes serve as cosmic recycling centers, breaking down complex structures into their fundamental components before potentially giving birth to new universes through quantum tunneling or white hole explosions. Greek mythology tells of Charybdis, the whirlpool monster that creates an inescapable vortex in the waters between Sicily and the Italian mainland. Ships that venture too close are drawn into spiraling paths that lead inevitably to destruction, much like matter falling into a black hole's accretion disk. The mythological whirlpool captures the essential geometry of gravitational capture, where approaching objects follow curved trajectories that end in consumption by an invisible force. Egyptian cosmology describes the Duat, an underworld realm accessible only through specific gateways and populated by beings that exist in states between life and death. The journey through the Duat involves passage through regions where normal physical laws do not apply, where time flows differently, and where travelers undergo fundamental transformations. These descriptions echo the experience of crossing a black hole's event horizon into a realm where space-time itself behaves according to alien principles. Australian Aboriginal Dreamtime stories speak of the rainbow serpent, a cosmic force that creates and destroys landscape features through its movements underground. This serpent can swallow entire mountains and rivers, making them disappear from the visible world while incorporating them into its vast body. The rainbow serpent's ability to make matter vanish while growing larger mirrors the way black holes consume visible matter and convert it into gravitational field energy. Mayan cosmology includes the concept of Xibalba, the place of fright that serves as both underworld and testing ground for souls, transitioning between states of existence. The journey to Xibalba involves crossing rivers of scorpions and blood, navigating houses filled with deadly trials, and ultimately facing tests that determine whether travelers will be transformed or destroyed. These trials resemble the extreme physics that operates near black hole event horizons, where matter must survive incredible forces to reach the interior. The Celtic otherworld of Anwen appears in Welsh mythology as a realm accessible through specific portals, often located in bodies of water or underground caverns. Time passes differently in Anwen, with visitors sometimes returning to find that centuries have elapsed in the ordinary world during what seemed like brief sojourns. This temporal distortion parallels the gravitational time dilation experienced near black holes, where time flows at dramatically different rates for different observers. Japanese Shinto tradition includes the concept of Wumi no Kuni, the land of the dead that lies beneath the surface of the ordinary world. Entry to Yomi occurs through specific gateways, but exit becomes increasingly difficult as travelers venture deeper into the realm. The mythology describes Yomi as a place where normal physical laws break down and where the very concepts of life and death lose their conventional meanings, similar to conditions inside black hole event horizons. Persian Zoroastrian cosmology describes Ahriman, the destructive force that seeks to devour all light and goodness in the universe. This cosmic devourer creates regions of absolute darkness where divine light cannot penetrate, consuming stars and planets to expand the domains of shadow. Ahriman's light-devouring properties directly parallel the defining characteristic of black holes, their ability to trap electromagnetic radiation within their event horizons. Native American traditions from various tribes describe cosmic monsters that live in the sky and consume celestial objects. The Cherokee tell of Uktana, a great serpent with supernatural powers that can swallow the sun and moon, creating eclipses and periods of darkness. These sky serpents often possess the ability to become invisible while retaining their gravitational influence on surrounding objects, much like the way black holes reveal their presence through effects on nearby stars and gas clouds. Mesopotamian mythology includes Tiamat, the primordial goddess of chaos, who represents the undifferentiated waters of creation and destruction. Tiamat's defeat by the god Marduk involves her body being split apart to create the heavens and earth, suggesting a connection between cosmic monsters and the fundamental structure of spacetime itself. This creation through destruction echoes theories that propose black holes as seeds for new universe formation. The recurring appearance of these themes across unrelated cultures suggests that the human psyche possesses an intuitive understanding of cosmic processes that modern science has only recently begun to quantify. The mythological imagination seems naturally drawn to concepts of ultimate boundaries, irreversible transformations, and the relationship between visible and invisible realms that form the essence of black hole physics. These ancient stories remind us that the quest to understand cosmic monsters represents more than mere scientific curiosity. It touches on fundamental human concerns about the nature of existence, the meaning of boundaries, and the relationship between order and chaos that have motivated philosophical and spiritual inquiry throughout history. At the heart of our Milky Way galaxy lurks a gravitational monster so massive that it contains 4 million times the mass of our Sun compressed into a region smaller than our solar system. This supermassive black hole, designated Sagittarius A*, pronounced Sagittarius a star, orchestrates the cosmic dance of hundreds of billions of stars, regulating the formation of new stellar systems, while slowly consuming the matter and energy that venture too close to its invisible boundary. Located 26,000 light-years away in the constellation Sagittarius, this cosmic giant reveals itself not through direct observation, but through the gravitational effects it exerts on its stellar neighborhood. Astronomers have watched stars orbit around the galactic center for decades, mapping their elliptical paths as they accelerate to tremendous speeds during their closest approaches to the central mass. These stellar motions provide direct measurement of the black hole's mass and location, with precision that rivals laboratory experiments. The most dramatic example of these orbital dynamics involves a star designated S2, which follows a highly elliptical path that brings it within just 120 times the distance between Earth and Sun at its closest approach to Sagittarius A*. During these periapsis passages, S2 accelerates to nearly 3% the speed of light, experiencing gravitational fields so intense that they create measurable distortions in spacetime itself. Einstein's theory of general relativity predicts specific effects for objects moving through such extreme gravitational fields. S2's orbit should precess, rotating slowly as the intense gravity of Sagittarius * curves the fabric of spacetime. This precession was detected with extraordinary precision by the Very Large Telescope in Chile, providing one of the strongest confirmations of general relativity under extreme conditions and ruling out alternative theories of gravity. The star's light also exhibits gravitational redshift as it climbs out of the black hole, gravitational well, during each orbit. Photons lose energy as they escape the intense gravitational field, arriving at Earth with slightly longer wavelengths than they possessed when emitted. This effect varies with the star's distance from the black hole, creating a precise test of Einstein's predictions about how gravity affects electromagnetic radiation. Surrounding Sagittarius lies a complex ecosystem of gas, dust, and stellar remnants that interact with the central black hole in violent and spectacular ways. The immediate vicinity contains hot, ionized gas that glows in radio wavelengths, creating the radio source that first revealed the black hole's presence to astronomers. This gas flows in complex patterns determined by magnetic fields, stellar winds, and the gravitational influence of the central monster. The black hole occasionally feeds on material from its surroundings, creating dramatic flares of X-ray and infrared radiation as matter heats up during its final spiral toward the event horizon. These feeding events can increase the black hole's luminosity by factors of hundreds within hours, then fade back to quiescent levels as the consumed material disappears beyond the point of no return. One of the most remarkable feeding episodes occurred in 2019 when Sagittarius A* experienced its brightest flare ever recorded, glowing 75 times brighter than normal in infrared wavelengths. The flare lasted only a few hours, but provided unprecedented insights into the physics of matter accretion onto supermassive black holes. The rapid variability of the emission suggests that material was orbiting just outside the event horizon, in the final moments before crossing the boundary. The Event Horizon Telescope has historic image of Sagittarius A** revealed the black hole shadow for the first time, showing the characteristic dark circle surrounded by glowing material in the accretion disk. The image confirmed theoretical predictions about the appearance of black holes and provided direct visual evidence for the Event Horizon's existence. The shadow size matched Einstein's predictions with remarkable precision, validating general relativity under the most extreme gravitational conditions observable in the universe. Creating this image required technological achievements that pushed observational astronomy to its limits. The rapidly varying emission from Sagittarius A* made it much more challenging to photograph than the relatively stable M87 black hole. The data had to be processed using sophisticated algorithms that could distinguish genuine structural features from the rapid fluctuations caused by turbulence in the surrounding gas. The supermassive black hole at our galaxy's center plays a crucial role in regulating star formation throughout the Milky Way. Its gravitational influence helps determine the orbital patterns of stars in the galactic bulge, while periodic outbursts of energy can heat gas clouds and suppress star formation in surrounding regions. This regulatory function appears to be common among supermassive black holes, suggesting that they serve as cosmic thermostats that control the evolution of their host galaxies. Sagittarius A* also serves as a laboratory for testing exotic physics under conditions impossible to replicate on Earth. The extreme gravitational fields near its event horizon create opportunities to study quantum gravity effects, test alternative theories of spacetime, and explore the relationship between black holes and quantum mechanics. Future observations may detect gravitational waves from material falling into the black hole or from the inspiral of smaller compact objects. The black hole's rotation rate remains an active area of investigation, with important implications for understanding its formation history and current energy output. Rapidly spinning black holes can extract rotational energy through the Penrose mechanism, potentially powering the relativistic jets and high-energy phenomena observed in other galaxies. Measuring Sagittarius A* spin requires precise observations of matter orbiting close to the event horizon. The discovery of other massive objects in the galactic center, including neutron stars and stellar mass black holes, creates a complex gravitational environment where multiple compact objects interact through their mutual gravitational attraction. These interactions can accelerate objects to extremely high velocities, potentially creating hypervelocity stars that escape the galaxy entirely, or exotic collision events that produce gravitational waves detectable by Earth-based instruments. Our galactic monster represents both opportunity and destination for future space exploration. While the enormous distances involved make direct visits impossible with current technology, robotic probes might someday venture into the galactic center to study Sagittarius A* at close range. Such missions would require breakthrough advances in propulsion and radiation shielding, but could provide unprecedented insights into black hole physics and the structure of spacetime itself. The continuing study of Sagittarius A promises to reveal new secrets about the nature of gravity, spacetime, and the fundamental physics that govern our universe. This monster in our backyard serves as a cosmic laboratory where the most extreme conditions in nature create opportunities for discovery that could revolutionize our understanding of reality itself. In the deepest realms of theoretical physics lies a possibility so extraordinary that it challenges our most fundamental assumptions about cosmic birth and death. The idea that every black hole might serve as a cosmic nursery, giving birth to entirely new universes, with their own dimensions, physical constants, and evolutionary histories. This mind-bending concept suggests that our observable cosmos might itself be the interior of a massive black hole existing within a larger parent universe. The theoretical foundation for black hole universe creation emerges from attempts to resolve the singularity problem that lies at the heart of general relativity. Classical physics predicts that matter falling into black holes eventually reaches points of infinite density and curvature, where mathematical description breaks down completely. But quantum gravity theories suggest that these infinities might be resolved through processes that connect black hole interiors to entirely separate spacetime regions. Picture the cosmic birth process through this revolutionary lens. When massive stars collapse to form black holes, the extreme gravitational compression might not terminate in a classical singularity, but instead trigger quantum tunneling events that create new spacetime bubbles. These bubbles expand into full-fledged universes, complete with their own big bangs, cosmic evolution, and potentially life-bearing worlds. From this perspective, black holes become cosmic reproductive organs rather than mere gravitational monsters. The mathematics supporting this scenario rely on modifications to Einstein's equations that incorporate quantum effects near the Planck scale. When matter compresses to densities approaching the fundamental quantum limit, the familiar geometry of spacetime breaks down and is replaced by quantum foam, where the concepts of distance and time lose their classical meanings. Within this foam, quantum fluctuations might create bridges to new spacetime regions that inflate into separate universes. Lee Smolin's cosmological natural selection hypothesis extends this idea to explain the apparent fine-tuning of physical constants in our universe. If black holes create daughter universes with slightly modified physics, then universes that produce many black holes will have more offspring than those that produce few. Over cosmic generations, this selection pressure would favor universes with physical constants optimized for black hole production, which coincidentally might also favor the formation of stars, planets, and life. This evolutionary cosmology predicts that our universe's physical constants should be nearly optimal for producing the maximum possible number of black holes consistent with other physical constraints. The masses of fundamental particles, the strength of nuclear forces, and the expansion rate of the universe would all reflect this cosmic selection pressure operating over countless generations of universe reproduction. The inflationary Big Bang model of our own cosmic origin gains new significance when viewed through the lens of black hole reproduction. The rapid expansion that occurred during the first fraction of a second after our universe's birth might represent the natural consequence of quantum tunneling from a black hole interior in a parent cosmos. The cosmic microwave background radiation that permeates our universe could carry subtle signatures of the black hole environment from which we emerged. Testing this hypothesis presents extraordinary challenges for observational cosmology. The parent universe, if it exists, remains completely inaccessible to observation or communication from within our cosmic bubble. The quantum tunneling process that connects black hole interiors to new universes operates at energy and timescales far beyond any conceivable experimental probe. We can never directly verify whether our universe emerged from a black hole or whether the black holes we observe give birth to cosmic offspring. However, indirect evidence might support and refute the black hole universe hypothesis through its predictions about the structure and evolution of our cosmos. If cosmic natural selection operates as Smolin proposed, then our universe's physical constants should show specific relationships that optimize black hole production while remaining consistent with observed physics. Deviations from these relationships could rule out the reproductive black hole model. The concept also predicts specific patterns in the cosmic microwave background that might distinguish inflation within a black hole from inflation in empty space. The quantum state of the pre-inflationary universe would differ between these scenarios, potentially creating detectable differences in the polarization patterns and spectral characteristics of the ancient radiation that fills our sky. Alternative approaches to black hole reproduction involve the creation of baby universes through processes that do not require complete space-time disconnection. These scenarios propose that black holes might create new cosmic regions that remain connected to the parent universe through microscopic wormholes. Such connections could allow limited information transfer between parent and offspring cosmos, potentially creating observable consequences. String theory provides additional mechanisms for black hole universe creation through the process of brain-world formation. In higher dimensional spacetime, black holes might represent defects in the fabric of space itself that spawn lower dimensional universes embedded within the larger cosmic structure. These daughter universes would possess their own gravitational and electromagnetic fields while remaining part of the higher dimensional parent cosmos. The holographic principle adds another layer of complexity to black hole reproduction by suggesting that the information content of black hole interiors might be encoded on their two-dimensional surfaces. If new universes form within black holes, their entire evolutionary history might be predetermined by the quantum information pattern impressed on the event horizon during formation. This would create a deterministic relationship between parent black hole properties and offspring universe characteristics. Loop quantum cosmology offers specific models for the bounce process that might occur within black holes, replacing classical singularities with quantum transitions to expanding spacetime regions. These models predict that the maximum density achieved during gravitational collapse remains finite, allowing matter and energy to pass through the compression phase and emerge into new cosmic expansion. The resulting universes would inherit modified versions of their parents' physical laws. The philosophical implications of black hole universe creation extend far beyond theoretical physics to fundamental questions about the nature of existence and cosmic purpose. If our universe emerged from a black hole in a parent cosmos, then the death of massive stars represents acts of cosmic reproduction rather than mere destruction. The monsters we fear might actually be the creators of countless worlds teeming with possibilities for life and consciousness. This perspective transforms black holes from endpoints of cosmic evolution into waypoints in an infinite reproductive cycle spanning multiple levels of reality. Our universe becomes one member of a vast cosmic family tree, with ancestors and descendants connected through the quantum tunneling, events that occur within gravitational singularities. The black holes we observe might even now be giving birth to universes where different versions of physics, chemistry, and biology unfold their own unique stories of cosmic evolution. Even the mightiest gravitational monsters, those cosmic behemoths that devour light itself, cannot escape the inexorable march toward their own destruction. Through a quantum mechanical process so subtle that it operates on timescales vastly exceeding the current age of the universe, black holes slowly evaporate by emitting thermal radiation that carries away their mass and energy. This gradual death represents one of physics' most profound discoveries, revealing deep connections between gravity, quantum mechanics, and thermodynamics. The discovery of black hole evaporation emerged from Stephen Hawking's investigation of quantum field theory in curved spacetime during the 1970s. Classical general relativity predicts that nothing can escape from within a black hole's event horizon, making these objects perfect absorbers of matter and energy. But quantum mechanics introduces fundamental uncertainties that create subtle violations of this classical prohibition. The quantum vacuum, far from being empty space, seethes with virtual particle pairs that spontaneously appear and disappear on microscopic timescales. These quantum fluctuations normally have no observable effects because the virtual particles annihilate each other before they can be detected. But near a black hole's event horizon, the intense gravitational field can separate virtual pairs before they recombine, promoting them to real particle status. Picture the process unfolding at the quantum level. A virtual particle pair materializes just outside the event horizon, with one member possessing positive energy and the other negative energy. The gravitational field pulls the negative energy particle toward the black hole, while allowing its positive energy partner to escape to infinity. The escaping particle becomes real Hawking radiation, while the negative energy particle falls into the black hole and reduces its total mass. This mechanism operates through the equivalence between mass and energy established by Einstein's special relativity. The negative energy particles absorbed by the black hole decrease its rest mass, while the positive energy particles that escape carry away the corresponding energy as thermal radiation. The process conserves total energy while gradually reducing the black hole's mass through quantum mechanical extraction. The temperature of Hawking radiation depends inversely on the black hole's mass, creating a counterintuitive relationship where smaller black holes burn hotter than larger ones. A black hole with the mass of our Sun would emit radiation at a temperature of only 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background that fills intergalactic space. Such black holes actually absorb more energy from their surroundings than they emit, causing them to grow rather than evaporate. But stellar mass black holes represent mere infants in the cosmic hierarchy of gravitational monsters. Supermassive black holes containing millions or billions of solar masses emit radiation at temperatures measured in trillionths of degrees, making their evaporation times incomprehensibly long. The supermassive black hole at our galaxy's center will require approximately 1,067 years to evaporate completely, a time span that dwarfs the current age of the universe by factors beyond human comprehension. Only primordial black holes formed in the early universe, with masses much smaller than stars, would emit significant Hawking radiation in the current cosmic epoch. These hypothetical objects, created by density fluctuations during the first moments after the Big Bang, could range from microscopic to mountain-sized masses. The smallest primordial black holes would evaporate almost instantaneously, while those with masses comparable to large asteroids might be completing their evaporation process today. The final stages of black hole evaporation create one of nature's most spectacular theoretical phenomena. As a black hole loses mass through Hawking radiation, its temperature increases exponentially, accelerating the evaporation process. The final moments involve a runaway process where the black hole's temperature soars to billions of degrees as its mass approaches zero. This terminal explosion would release the remaining energy in a burst of high-energy particles and gamma radiation. The detection of such evaporation events would provide direct confirmation of Hawking as theoretical predictions while offering insights into quantum gravity and the ultimate fate of matter in the universe. Gamma-ray observatories scan the sky for the distinctive signatures that primordial black hole explosions would create. Though no convincing detections have been reported, the absence of observed explosions places constraints on the abundance of primordial black holes in our cosmic neighborhood. Hawking radiation carries profound implications for the relationship between black holes and thermodynamics. The discovery that black holes emit thermal radiation at definite temperatures revealed them to be genuine thermodynamic systems, obeying the same statistical laws that govern gases, liquids, and other forms of matter. This connection established black hole thermodynamics as a fundamental bridge between gravity and statistical mechanics. The entropy of a black hole, measured by the area of its event horizon rather than its volume, represents one of the most surprising discoveries in theoretical physics. This relationship suggests that information might be fundamentally two-dimensional rather than three-dimensional, encoded on surfaces rather than distributed throughout volumes. The holographic principle that emerges from this insight has revolutionized theoretical approaches to quantum gravity and cosmology. The information content carried by Hawking radiation remains one of physics' most contentious issues. Hawking's original calculations suggested that the emitted radiation is completely thermal, carrying no information about the matter that formed the black hole. This prediction creates the information paradox, since quantum mechanics requires that information be preserved throughout all physical processes, including black hole formation and evaporation. Recent theoretical developments have suggested that Hawking radiation might carry subtle quantum correlations that preserve information about the black hole as contents. These correlations would be extraordinarily difficult to detect, requiring measurements of incredible precision across vast numbers of radiation particles. But their existence would resolve the information paradox while maintaining the fundamental principles of both quantum mechanics and general relativity. The evaporation process also affects the structure of space-time around black holes in ways that remain poorly understood. As black holes lose mass, their event horizons shrink and their curvature of space-time decreases. The quantum fields that produce Hawking radiation exist in highly non-trivial quantum states that might create observable effects on the geometry of space and time near the evaporating black hole. Future observations of black hole evaporation might reveal entirely new physics operating at the intersection of quantum mechanics and gravity. The extreme conditions created during the final stages of evaporation could produce exotic particles, reveal extraspatial dimensions, or demonstrate quantum effects in space-time geometry. These phenomena would provide unprecedented tests of theories that attempt to unify gravity with the other fundamental forces. The slow death of black holes through Hawking radiation represents more than just another exotic physics phenomenon. It demonstrates the ultimate triumph of quantum uncertainty over classical determinism, showing that even the most perfect traps in the universe cannot permanently contain the quantum fluctuations that permeate all of reality. In the end, every black hole must surrender to the persistent whisper of quantum mechanics, evaporating particle by particle until nothing remains but the fading glow of thermal radiation dispersing into the cosmic void. The moment arrives with deceptive calm. Perhaps your spacecraft has suffered catastrophic failure near the invisible monster, or perhaps you have chosen this ultimate journey deliberately, seeking to experience the universe's most extreme physics firsthand. Regardless of how you arrived at this point, the laws of nature now govern your inexorable descent into the cosmic abyss, creating an experience unlike anything else in the universe. Your journey begins at a comfortable distance from the black hole, where its gravitational influence feels no stronger than that of any other massive celestial body. Your instruments detect no unusual acceleration, no dramatic forces pulling you toward the invisible center. The stars maintain their familiar patterns, and the cosmic background appears normal in every respect. Yet you have crossed an invisible threshold, entering the black hole's sphere of influence, where its gravity will ultimately dominate all other forces. As you fall deeper into the gravitational well, the first subtle effects begin to manifest themselves. Your feet, slightly closer to the black hole than your head, experience marginally stronger gravitational acceleration. This differential creates the gentlest of stretching sensations, like the feeling of hanging from a horizontal bar, but oriented vertically toward the source of gravity. The effect remains barely perceptible at large distances, but it marks the beginning of the tidal forces that will eventually reshape your entire body. The view around you starts to transform in ways that challenge human perception. Light from stars directly ahead appears slightly bluer as your increasing velocity toward the black hole creates Doppler shifts in the electromagnetic radiation. Behind you, starlight grows redder as photons stretch to longer wavelengths. The cosmic microwave background begins to show similar patterns, creating a faint temperature gradient across the sky that grows more pronounced as your speed increases. Time dilation effects become increasingly significant as you descend deeper into the gravitational field. Your personal timekeeper continues ticking at its normal rate, but if you could somehow observe clocks located far from the black hole, you would see them racing ahead at accelerating pace. Minutes on your watch correspond to hours, then days, then years in the external universe, as gravitational time dilation approaches extreme values. The black hole's event horizon approaches without any visual indication of its presence. Space appears empty and normal, offering no warning about the cosmic point of no return that lies ahead. Your instruments cannot detect the boundary's location through local measurements, since the event horizon exists as a geometric property of spacetime rather than a physical barrier made of matter or energy. As you near the horizon, the tidal stretching becomes more pronounced. Your spine feels gentle elongation as the differential gravitational forces grow stronger. Blood circulation begins to show effects as your cardiovascular system struggles against the gravitational gradient that pulls fluid toward your feet. Your head grows light while your extremities swell under increased hydrostatic pressure. The view behind you undergoes dramatic transformation as the entire external universe compresses into an increasingly bright and narrow ring of light. Gravitational lensing focuses all the stars, galaxies, and nebulae in the cosmos into this brilliant Einstein ring, concentrating the light of billions of celestial objects into a circle that grows smaller and more intense as you approach the event horizon. The moment of crossing the event horizon passes without ceremony. No sensation marks your passage across this ultimate boundary. No alarm sounds to indicate that you have entered a region from which no escape is possible. Your subjective experience remains continuous and unremarkable, though you have crossed from a domain where communication with the external universe remains theoretically possible to one where it does not. Yet the physics of your situation has fundamentally changed. Every possible future trajectory available to you now leads inexorably inward toward the central singularity. The geometry of space-time itself has been so thoroughly curved by the black hole as mass that outward directions no longer exist within your local reference frame. You continue falling through what appears to be empty space, but space itself has been transformed into a cosmic funnel with only one possible destination. The tidal forces continue to strengthen as you approach the singularity. For a stellar mass black hole, these forces become lethal while you still fall through the interior, stretching your body beyond the breaking point of biological structures. Your skeleton elongates as vertebrae separate under differential gravitational stress. Organs compress and stretch as the gradient forces overwhelm the electromagnetic bonds holding complex molecules together. The stretching accelerates exponentially as the singularity approaches. Your body assumes increasingly unnatural proportions, growing longer and thinner like a piece of taffy being pulled by invisible hands. Blood vessels rupture under the strain. Nerve connections sever as tissues stretch beyond their elastic limits. The familiar chemistry of life gives way to physics operating under conditions never encountered anywhere else in nature. At the molecular level, the tidal forces eventually overcome even the electromagnetic forces that hold atoms together. Protein molecules denature as their complex three-dimensional structures collapse under gravitational stress. DNA strands snap like overstretched cables. Individual atoms stretch into exotic configurations as electron orbitals distort under the influence of the extreme tidal gradients. Throughout this process, your perception of the external universe continues to evolve. The compressed ring of light behind you grows smaller and more intense, potentially becoming so energetic that it would be lethal even without the tidal effects. In principle, this ring contains information about the entire future history of the external universe, compressed into the final moments of your journey toward the singularity. The final approach to the singularity enters regimes where human language and even mathematical description begin to fail. Classical general relativity predicts infinite density and curvature, conditions so extreme that they transcend physical law as we understand it. Quantum effects that normally operate on microscopic scales expand to encompass your entire experience as space-time itself breaks down into quantum foam. Your journey represents more than personal destruction. It becomes a voyage into the fundamental limits of physical knowledge, where the boundaries between matter and energy, space and time, existence and non-existence dissolve into quantum uncertainty. The information that once described your complex biological structure becomes encoded in quantum correlations that may persist even as classical descriptions lose all meaning. The human experience of falling into a black hole ultimately transcends the merely physical to become a meditation on the nature of existence itself. At the moment when tidal forces reduce your complexity to elementary particles in quantum fields, you join the countless particles, planets, and stars that have made this same journey throughout cosmic history, becoming part of the mystery that lies at the heart of every black hole. Your fall concludes not with answers, but with participation in the universe's deepest question. What lies beyond the boundaries of spacetime itself? Far from being mere cosmic vacuum cleaners that indiscriminately consume everything in their vicinity, black holes serve as the universe's master architects, shaping the evolution of galaxies across billions of years and regulating the formation of stars, planets, and the chemical elements that make life possible. These gravitational monsters orchestrate cosmic construction projects on scales so vast that they influence the structure of spacetime itself across millions of light years. At the heart of nearly every large galaxy lies a supermassive black hole containing millions or billions of times the mass of our Sun. These central monsters maintain a delicate gravitational relationship with their surrounding stellar populations, creating what astronomers call the bulge black hole correlation. The mass of the central black hole directly relates to the mass of stars in the galactic bulge, suggesting that black holes and their host galaxies evolve together through intimate feedback mechanisms. This cosmic symbiosis operates through processes that connect the smallest scales of black hole physics to the largest scales of galactic structure. As matter falls toward a supermassive black hole, it forms an accretion disk that converts gravitational potential energy into electromagnetic radiation with extraordinary efficiency. The resulting luminosity can exceed the combined output of all the stars in the host galaxy, creating what astronomers observe as active galactic nuclei and quasars. But the energy output represents only one aspect of the black hole's influence on galactic evolution. The intense radiation and high-energy particles produced by active accretion can heat gas throughout the galaxy to temperatures of millions of degrees, preventing it from cooling and condensing to form new stars. This feedback mechanism allows black holes to regulate star formation rates across their entire galactic domains, acting as cosmic thermostats that control the pace of stellar birth. Relativistic jets launched from the vicinity of rotating supermassive black holes carry this influence even further into intergalactic space. These narrow beams of plasma, accelerated to nearly the speed of light by magnetic fields threading through the black hole's ergosphere, can extend for millions of light years beyond the galaxy's visible boundaries. The jets deposit enormous amounts of energy into the surrounding medium, heating gas clouds and preventing them from falling back into the galaxy. The jets also serve as cosmic particle accelerators, creating the highest energy cosmic rays observed in the universe. These ultra-high energy particles carry energies that exceed anything achievable in human-built accelerators by factors of millions, providing natural laboratories for testing physics under extreme conditions. When these particles interact with magnetic fields and radiation throughout the galaxy, they create complex webs of energy that influence star formation across vast regions. The regulatory influence of supermassive black holes extends to the chemical evolution of their host galaxies through control of stellar life cycles. By modulating star formation rates, black holes determine how quickly massive stars form, leave, and die in supernova explosions that scatter heavy elements throughout interstellar space. This process of stellar nucleosynthesis creates the carbon, oxygen, silicon, iron, and other elements essential for rocky planet formation and biological chemistry. During periods of active feeding, supermassive black holes can trigger dramatic changes in galactic structure through gravitational interactions with stellar orbits. The massive gravitational perturbations created by black hole growth can scatter stars into new orbital configurations, reshape galactic bars and spiral arms, and even eject stars from their parent galaxies entirely. These hypervelocity stars carry information about black hole activity as they travel through intergalactic space. The growth history of supermassive black holes parallels the cosmic evolution of structure formation in the universe. The first black holes likely formed from the collapse of the universe's first generation of massive stars, creating seed black holes with masses of hundreds of solar masses. These seeds grew through accretion of surrounding matter and mergers with other black holes, eventually reaching the supermassive scales observed today. Black hole mergers represent some of the most violent events in the universe, releasing more energy and gravitational waves than all the stars in the observable universe emit in electromagnetic radiation. These cosmic collisions reshape spacetime itself, sending ripples through the fabric of space that carry information about black hole properties across billions of light years. The detection of these gravitational waves has opened new windows into black hole physics and galactic evolution. The merger process also demonstrates the hierarchical nature of structure formation in the cosmos. Smaller galaxies containing intermediate mass black holes merge to form larger galaxies with more massive central black holes. This process of galactic cannibalism, mediated by black hole interactions, creates the diverse population of galaxy types observed in the modern universe, from dwarf ellipticals to giant CD galaxies containing hundreds of trillions of stars. Binary supermassive black holes, formed when galaxies merge, but their central black holes have not yet coalesced, create some of the most exotic gravitational environments in the universe. These systems can eject stars through gravitational slingshot effects, carve central cavities in galactic stellar distributions, and eventually merge to produce the strongest gravitational wave signals detectable by space-based observatories. The influence of black holes on galactic architecture operates across multiple scales simultaneously. Local effects near the event horizon influence matter within light hours of the central monster. Accretion disk physics operates on scales of light days to light years. Jet propagation affects regions spanning thousands of light years, and the overall gravitational influence of the black hole shapes stellar orbits across the entire galaxy, encompassing hundreds of thousands of light years. Recent observations have revealed that some galaxies lack central supermassive black holes, while others contain multiple massive black holes in complex orbital configurations. These variations provide natural experiments for understanding the role of black holes in galactic evolution, allowing astronomers to compare galaxies with different black hole populations and trace the effects of these gravitational monsters on cosmic structure formation. The study of black holes as galactic architects has revealed deep connections between quantum physics operating near event horizons and the large-scale structure of the universe. The same physical processes that govern Hawking radiation and information preservation also influence the formation of stars, planets, and potentially life itself across cosmic scales that span dozens of orders of magnitude in size and time. Understanding black holes as cosmic architects transforms our perspective on these gravitational monsters from destructive forces to creative agents that shape the universe's evolution toward increasing complexity and organization. They represent nature's most efficient engines for converting gravitational potential energy into the electromagnetic radiation, high-energy particles, and complex gravitational fields that drive galactic evolution across billions of years of cosmic time. Across the vast emptiness of intergalactic space travel invisible messengers that carry tales of cosmic violence from the universe's most extreme environments. These gravitational waves, ripples in the fabric of spacetime itself, originate from cataclysmic events involving black holes and propagate at the speed of light across billions of years and countless light years to reach Earth's sensitive detectors. Each wave carries encoded information about collisions between gravitational monsters that occurred when the universe was younger and the cosmic landscape looked entirely different from today. The detection of gravitational waves represents one of humanity's greatest scientific achievements, confirming Einstein's boldest prediction about the dynamic nature of spacetime and opening entirely new windows into cosmic phenomena that remain invisible to traditional astronomy. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through everything unchanged, carrying pristine information from their sources directly to our instruments. The first gravitational wave detection, announced in February 2016, revealed the collision and merger of two black holes with masses approximately 30 times that of our Sun, located over 1 billion light-years away. The signal, designated GW150914, lasted only a fraction of a second, but contained enough information to reconstruct the entire merger process from the final moments of orbital decay to the violent collision and the ring-down of the resulting larger black hole. This cosmic collision released more energy in gravitational waves than all the stars in the observable universe emit in electromagnetic radiation. Yet the effect on space-time geometry at Earth amounted to a change in distance smaller than 1/10,000th the width of a proton. The detection required interferometers with arm lengths of several kilometers and laser systems capable of measuring length changes smaller than the quantum uncertainty in photon positions. Subsequent detections have revealed a diverse population of black hole mergers spanning a wide range of masses, spins, and orbital configurations. Some mergers involve black holes with similar masses spiraling into each other from nearly circular orbits. Others feature highly asymmetric systems where one black hole significantly outmasses its companion, or highly eccentric orbits that create complex gravitational wave patterns as the separation distance varies dramatically. The gravitational wave signatures encode detailed information about the physics operating in the strongest gravitational fields that exist in the universe. As black holes spiral toward merger, they reach orbital velocities approaching significant fractions of the speed of light, while separated by distances of only hundreds of kilometers. The extreme curvature of spacetime in these systems creates conditions where general relativity operates far from the weak field regime tested by most other experiments. These observations have provided unprecedented tests of Einstein's theory under conditions billions of times more extreme than anything accessible through solar system experiments. The detected waveforms match theoretical predictions with extraordinary precision, confirming general relativity's accuracy in regimes where alternative theories of gravity predict significant deviations. The consistency between theory and observation validates our understanding of spacetime dynamics under the most extreme conditions nature provides. The merger process itself reveals fascinating physics about how black holes combine to form larger monsters. When two event horizons approach each other, they deform dramatically under mutual gravitational influence before eventually joining to create a single, larger event horizon. The resulting black hole oscillates like a ringing bell, emitting gravitational waves with frequencies and decay rates determined by its final mass and spin properties. This ring-down radiation provides direct measurements of the newly formed black hole's characteristics and tests whether the merger product behaves exactly as general relativity predicts. Any deviations from expected ring-down patterns could reveal new physics beyond Einstein's theory or exotic objects that masquerade as black holes but possess different internal structures. Gravitational wave astronomy has also revealed surprising aspects of black hole formation and evolution throughout cosmic history. The detected black hole masses often exceed theoretical predictions from stellar evolution models, suggesting that some black holes form through alternative mechanisms such as direct collapse in the early universe or growth through accretion processes that operate differently than previously thought. The detection of neutron star mergers through gravitational waves has provided insights into the equation of state of matter at nuclear densities and the origin of heavy elements in the universe. When two neutron stars spiral into each other, they create both gravitational waves and electromagnetic signals across the entire spectrum from radio waves to gamma rays, allowing multi-messenger astronomy that combines gravitational and electromagnetic observations. These neutron star mergers also create the conditions necessary for rapid neutron capture nucleosynthesis, the process that creates many of the universe's heaviest elements, including gold, platinum, and uranium. The gravitational wave detection, GW170817, accompanied by optical observations of the resulting kilonova explosion, provided direct evidence that neutron star mergers serve as cosmic element factories that enrich the interstellar medium with materials essential for planetary formation. Future gravitational wave observatories will extend detection capabilities to include a much broader range of black hole masses and cosmic distances. Space-based detectors like the planned Laser Interferometer Space Antenna, LISA, will observe supermassive black hole mergers occurring throughout the universe, providing insights into how the largest gravitational monsters form and evolve over cosmic time. These observations will reveal the merger trees that connect stellar mass black hole formation to supermassive black hole growth, tracing the evolutionary pathways that lead from the deaths of the first stars to the formation of the massive monsters that regulate galaxy evolution. The gravitational wave signals from supermassive black hole mergers can be detected years or decades before the final coalescence, providing advance warning of these spectacular cosmic events. Gravitational wave astronomy has also opened possibilities for detecting exotic objects and phenomena that remain purely theoretical. Primordial black holes formed in the early universe cosmic strings left over from phase transitions in the first, moments after the Big Bang, or even signatures of extra dimensions could all produce distinctive gravitational wave signatures that would revolutionize our understanding of fundamental physics. The continuing development of gravitational wave astronomy promises to transform black hole physics from a largely theoretical field into an observational science with direct access to the most extreme environments in the universe. Each detected signal carries information from regions where space-time curvature reaches maximum values and quantum effects might become observable in gravitational phenomena. The echoes of the abyss that reach Earth through gravitational wave detectors provide humanity with a new sense, a way of feeling the vibrations of space-time itself as massive objects accelerate through the strongest gravitational fields that exist. These cosmic reverberations connect us directly to the violence and beauty of black hole physics, allowing us to witness events so extreme that they reshape the very geometry of reality itself. As we stand at the threshold between the known and unknowable, between the regions where physics provides answers and the realms where only questions exist, the experience of falling into a black hole transcends mere scientific inquiry to become a profound meditation on the nature of existence knowledge and the boundaries of human understanding. Here, at the edge of the cosmic abyss, physics transforms into philosophy and science merges with wonder. The journey into a black hole challenges our most fundamental assumptions about the relationship between observer and observed, between subjective experience and objective reality. From the perspective of the falling observer, the passage across the event horizon involves nothing more dramatic than continued motion through apparently empty space. Time flows normally, physical sensations remain comprehensible, and the local environment obeys familiar laws of physics right up until tidal forces become overwhelming near the singularity. Yet from the viewpoint of external observers, this same journey never concludes. The falling traveler appears to slow dramatically as they approach the event horizon, their image growing redder and dimmer until it fades beyond detection. To outside observers, the fall takes infinite time, frozen forever at the boundary between escape and entrapment. These radically different descriptions of the same physical event challenge the notion that reality possesses a single, objective character independent of observational perspective. This observer-dependent nature of black hole physics reflects deeper philosophical questions about the role of consciousness in determining physical reality. Does the falling observer actually cross the event horizon and experience the interior of the black hole, or do they remain forever frozen at the boundary as external observers perceive. Both descriptions emerge from valid applications of general relativity, yet they seem to describe fundamentally different realities. The information paradox that emerges from black hole physics touches on even more fundamental questions about the nature of identity, memory, and the persistence of information through physical transformations. If the information that defines your molecular structure, your memories, your consciousness becomes encoded in Hawking radiation through quantum correlations too subtle to decode, in what sense do you continue to exist? Does information preservation through quantum entanglement constitute a form of immortality, or merely a mathematical abstraction with no relationship to conscious experience? These questions connect black hole physics to ancient philosophical puzzles about personal identity and the ship of Theseus paradox. If every atom in your body is replaced gradually over time while preserving the pattern of organization that defines your consciousness, do you remain the same person? If black hole evaporation preserves your information content in quantum correlations spanning light years of Hawking radiation, does this quantum ghost bear any meaningful relationship to your original self? The singularity at the black hole's center represents perhaps the ultimate confrontation between human reason and cosmic mystery. Here, mathematical description breaks down completely, infinities proliferate without resolution, and the predictive power of physical law surrenders to fundamental uncertainty. Yet this mathematical failure might reveal deeper truths about the limitations of rational thought when confronted with ultimate questions about existence. The approach to infinite density and curvature forces us to confront whether the universe possesses aspects that transcend mathematical description entirely. Perhaps the singularity represents not a failure of physics, but a boundary where physical law connects to realms of being that cannot be captured through quantitative analysis. The breakdown of space-time geometry might mark the transition from the domain of science to territories that require different modes of understanding. Black holes also embody profound questions about the relationship between time and eternity, between finite existence and infinite duration. The gravitational time dilation that stretches moments into eons near the event horizon suggests that subjective experience of time bears little relationship to coordinate time measured by distant observers. From this perspective, the brief moments of falling across the event horizon might subjectively contain infinite duration, transforming finite existence into eternal experience. The cosmic role of black holes as recyclers of matter and information, as potential creators of new universes through quantum tunneling, suggests that destruction and creation represent complementary aspects of a deeper cosmic process. The monsters that appear to represent ultimate endings might actually serve as cosmic transformation engines, converting complexity into simplicity before enabling new forms of complexity to emerge from quantum uncertainty. This cyclical view of cosmic evolution through black hole processes connects to ancient philosophical and religious traditions that emphasize the interplay between creation and destruction, between manifestation and dissolution. The Hindu concept of cosmic cycles, the Buddhist notion of emptiness giving rise to form, the alchemical tradition of dissolution and reconstitution all find echoes in modern black hole physics. The holographic principle that emerges from black hole thermodynamics suggests even more radical revisions to our understanding of reality's fundamental structure. If three-dimensional space represents an emergent illusion arising from information encoded on two-dimensional surfaces, then the solid reality we perceive through our senses might be no more fundamental than the images projected by a hologram. Black holes become windows into the deeper nature of spacetime as information rather than substance. The quantum entanglement relationships that preserve information during black hole evaporation point toward a universe where separation and connection represent different aspects of an underlying unity. The correlations that span light years of space and billions of years of time suggest that individual existence might be less fundamental than the quantum relationships that connect all particles and events across the cosmos. From this perspective, falling into a black hole becomes not an isolated individual experience, but participation in the universal web of quantum correlations that underlies all of reality. The dissolution of personal identity through tidal forces and quantum decoherence might represent return to a more fundamental state of cosmic consciousness that transcends the boundaries of individual existence. The contemplation of black hole physics ultimately leads to recognition that the universe contains mysteries that may forever exceed human comprehension, not because of limitations in our instruments or theories, but because of the inherent boundaries between finite minds and infinite reality. The cosmic monsters that populate our universe serve as reminders of the vast realms of existence that remain beyond our intellectual grasp. Yet this recognition of mystery need not lead to despair or intellectual defeat. Instead, it can inspire wonder, humility, and appreciation for the profound privilege of conscious beings capable of contemplating their own cosmic context. The fact that matter organized into human brains can ponder the nature of black holes, can trace the mathematics of space-time curvature, can detect gravitational waves from cosmic collisions billions of years in the past, represents one of the universe's most remarkable achievements. As our impossible journey draws to its conclusion, we find ourselves transformed by the encounter with cosmic mystery. Having witnessed firsthand the universe's most extreme physics while exploring the boundaries between the knowable and unknowable, we have fallen through event horizons of understanding, stretched by tidal forces of wonder, and approached singularities where knowledge itself approaches infinite density and curvature. The black holes we have explored together represent far more than exotic solutions to Einstein's equations or astrophysical objects cataloged in distant galaxies. They embody the universe's deepest teachings about the nature of reality, time, information, and the fundamental structures that govern existence itself. Through studying these cosmic monsters, we have discovered that they serve simultaneously as destroyers and creators, as endpoints of stellar evolution and potential birthplaces of new universes. Our journey began with simple questions about what would happen if you fell into a black hole, but it led us to profound insights about the nature of space-time, quantum mechanics, and the role of information in physical law. We discovered that black holes possess temperature and entropy, that they evaporate through quantum processes operating near their event horizons, and that they might preserve information through correlations too subtle for current technology to decode. We witnessed the birth of black holes in the violent deaths of massive stars, traced their anatomy from event horizons to accretion disks to relativistic jets, and observed their shadows cast against the glowing backgrounds of their prey. We explored the paradoxes they create for our understanding of information conservation, causality, and the relationship between quantum mechanics and general relativity. The theoretical landscapes we navigated revealed possibilities that challenge human imagination. Traversable wormholes connecting distant regions of spacetime, white holes that spew matter and energy instead of consuming them, micro-black holes that might form in particle accelerators or cosmic ray interactions, and primordial black holes that could be evaporating throughout the cosmos in bursts of high-energy radiation. We discovered that these gravitational monsters serve as architects of cosmic structure, regulating star formation throughout their host galaxies while launching jets of plasma across millions of light years. Their mergers create the strongest sources of gravitational waves in the universe, sending ripples through spacetime that carry information about cosmic violence across billions of years of light travel time. The mythological connections we explored revealed that human imagination has always been drawn to concepts that modern physics recognizes in black holes: cosmic devourers, light-swallowing serpents, endless pits that serve as gateways between different realms of existence. These ancient stories suggest that the human psyche possesses intuitive understanding of cosmic processes that science has only recently begun to quantify. Our exploration of the philosophical implications revealed black holes as teachers of profound lessons about the nature of existence knowledge, and mystery. They challenge our assumptions about objective reality, force us to confront the limitations of rational thought, and suggest that consciousness might play fundamental roles in determining the character of physical reality itself. The time dilation effects we experienced near black holes demonstrated the malleable nature of temporal experience, showing that time flows differently depending on gravitational environment and relative motion. The minutes we spent falling toward the event horizon corresponded to eons in the external universe, revealing time not as absolute measure, but as coordinate that depends on observer and context. Perhaps most remarkably, we discovered that black holes might create new universes through quantum processes operating near their central singularities. This possibility transforms these cosmic monsters from mere endings into beginnings, from gravitational graves into cosmic wombs that give birth to entirely new realms of existence with their own physical laws and evolutionary histories. The information paradox that black holes create continues to drive theoretical physics toward deeper understanding of quantum gravity, holographic principles, and the fundamental nature of space-time itself. The resolution of this paradox will likely require insights that transform our understanding of reality at its most basic level, potentially revealing that space and time emerge from more fundamental quantum information processes. The gravitational wave astronomy that black holes have enabled provides humanity with entirely new senses for exploring the cosmos, allowing us to feel the vibrations of space-time itself as massive objects accelerate through extreme gravitational fields. Each detected signal carries pristine information from regions where physics operates under conditions impossible to replicate on Earth. Yet for all we have learned about black holes through decades of theoretical investigation and recent observational breakthroughs, they remain fundamentally mysterious. The singularities hidden within their event horizons continue to mark boundaries where physical law encounters its own limitations. The quantum processes that govern their evaporation operate on scales and timescales and may forever exceed direct experimental verification. This persistent mystery should not discourage us, but rather inspire continued wonder and investigation. Black holes remind us that the universe contains phenomena that exceed human comprehension, not because of temporary limitations in our knowledge, but because of fundamental boundaries between finite minds and infinite reality. They teach us humility while inspiring us to push the boundaries of understanding as far as possible. The journey we have taken together through the physics and philosophy of black holes represents more than intellectual exercise. It reflects humanity's deepest drive to understand our cosmic context, to trace the connections between quantum mechanics and relativity, between mind and matter, between the observed and the observer. Black holes serve as cosmic laboratories where these connections reveal themselves with unprecedented clarity. As we conclude this exploration, we are left not with definitive answers, but with deeper appreciation for the profound questions that black holes pose. What lies beyond the event horizon of human knowledge? How do consciousness and cosmos relate at the deepest level? What mysteries await discovery as our instruments become more sensitive and our theories more sophisticated? The black holes that populate our universe stand as eternal reminders that reality contains depths that may forever exceed our grasp, while simultaneously inspiring us to reach ever further toward understanding. They represent the universe's way of preserving mystery while rewarding curiosity, of maintaining wonder while enabling discovery. In the end, black holes teach us that the most profound truths often emerge not from answers, but from better questions, not from certainty, but from sustained engagement with mystery. They invite us to embrace the unknown, not as defeat, but as opportunity, to find meaning not in final explanations, but in the endless journey of exploration itself. The cosmic monsters we have encountered together will continue their ancient dance through space-time, long after human civilization has passed into history. But through our brief encounter with their mystery, we have participated in something eternal, the universe as ongoing attempt to understand itself through the consciousness it has created within us. If this journey through the physics and mystery of black holes has inspired you to look up at the night sky with new wonder to appreciate the profound connections between quantum mechanics and cosmic structure, or simply to embrace the beautiful mystery of existence itself, then we have succeeded in our impossible mission to fall into the abyss and return with tales of what we found there. The horizons of knowledge continue to expand, but they will always reveal new horizons beyond them. In that endless expansion of wonder lies perhaps the deepest truth that black holes have to teach us, that mystery and understanding are not opposites, but partners in the eternal dance of consciousness exploring cosmos.